People say that the Milky Way is our home, but what if we told you that it's not even the most interesting galaxy nearby? The Triangulum Galaxy is only 2.7 million light-years away. It is a beautiful galaxy, but its bigger brother, Andromeda, gets more attention. But don't believe it. This galaxy isn't as big as the Milky Way, but it packs a powerful punch. It has star factories bigger than any in the Milky Way, spiral arms full of new suns, and secrets that could change the way we think about galaxies in general. Welcome to M33, a place where stars are born in powerful waves, supernovae cut out gas tube, and the pulse of Cepheid variables tells us the time. This is more than just a trip through another twisting galaxy. It's right there in front of you, just beyond the constellation Triangulum. This is the raw engine of cosmic development. Where is M33, mapping the Triangulum Galaxy in our cosmic neighborhood? Take a step back from Earth, beyond the Moon, Mars-like, through the whole solar system. You are now more than 2 million light-years away from home. This is the Triangulum Galaxy, which is also called M33. It is floating quietly in the dark sea of the local group. In our galaxy's neighborhood, it's the third biggest, after the very big Andromeda galaxy and our own Milky Way. Also, Triangulum is not a background player, even if it doesn't get as much news. It's one of the most interesting places in the galaxy that we've ever looked through a lens. M33 lies in the constellation Triangulum, which gives the galaxy its name. From Earth, its apparent size is about the width of the full moon if you had superhuman night vision, but in reality, this thing spans over 60,000 light-years, roughly 60% the diameter of the Milky Way, and it's located at a distance of about 2.73 million light-years from Earth, as measured by variable stars known as Cepheids. That might sound far, but in cosmic terms, it's basically our next-door neighbor. Astronomers classify M33 as a spiral galaxy, but not like the tidy textbook spirals we often see. It's what's called an sac type, a loosely wound, unbarred spiral with no central bulge. That makes it kind of weird. No bar, no fat core, just a swirling disk with delicate arms. This unique shape means M33 provides a cleaner view into the process of star formation. Free from the chaos of a crowded core or a dominant black hole, it's almost like a stripped-down version of a spiral galaxy, a cosmic open floor plan. Triangulum also has a gravitational relationship with its big brother, Andromeda. These two galaxies are bound by gravity and may have already danced past each other in the distant past. There's evidence of tidal warping and a halo of stripped stars between them, hinting at a long and possibly violent history of interaction. And in the far future, maybe 4 or 5 billion years from now, Triangulum may even be devoured by Andromeda altogether during the epic merger of the local group's major players. Some simulations suggest that Triangulum might not just be a satellite of Andromeda. It could be its former partner in a galactic binary system. Like two celestial ice skaters locked in orbit, they may have once shared material, triggered starbursts, and carved each other's spiral arms with gravitational pull. That's one of the reasons scientists study M33 so obsessively. It's a live-action reel of how galaxies grow, fight, collide, and evolve. One thing that makes Triangulum different from the Milky Way and Andromeda is that it is facing us. Astronomers can see the whole disk of the star without much trouble because it is tilted at just the right angle, about 54 degrees from our line of sight. You don't have to look through thick gas clouds or dust lanes that touch each other. Instead, it's like looking straight down at a spiral galaxy from above, which is laid out like a cosmic plan. Because of its clarity, M33 is a great place to map. Its hydrogen gas has been tracked in great detail, showing the galaxy's full spin curve. That information about spin helps scientists figure out how much dark matter there is. Dark matter is an invisible material that surrounds galaxies like scaffolding and has an effect on their gravitational pull. M33, like our own galaxy, spins too quickly for the matter we can see to explain. This suggests that there is a ring of dark matter around the galaxy that goes far beyond its bright stars. M33 is also relatively metal-poor compared to the Milky Way. In astronomy, metals means any element heavier than helium, so lower metallicity implies that Triangulum has had fewer generations of star formation, or at least less recycling of material. This gives it an almost younger sibling vibe, less evolved, more pristine, and ideal for studying early galactic behavior. It also plays a part in the local group. Triangulum may be small, but it's strong. It has more than 40 billion stars, which makes it an important piece of information for studying how galaxies interact with each other on a large scale. It holds up one side of a cosmic triangle made up of the Milky Way, Andromeda, and M33. This triangle defines the gravity shape of our local universe. So, why does M33 matter? Because it's close, it's clean, and it's weird. It's a galactic petri dish that astronomers use to test everything from star formation and spiral arm dynamics to black hole presence and dark matter distribution. And thanks to modern telescopes, from the Hubble Space Telescope to ALMA and beyond, we're mapping it in ways that were science fiction just a decade ago. The shape of a spiral, how Triangulum's arms are wound. Most galaxies move through space like cosmic whirlpools, which are huge, beautiful swirls that wrap around a bright center. But Triangulum, it has its own vibe. It doesn't have tight, symmetrical spiral arms like the Milky Way. Astronomers call M33 one of the most interesting examples of a flocculent spiral because its spiral arms aren't tightly wound. Instead, they're broken up and a bit disorganized. To begin, let us talk about pitch angle. In this direction, the spiral arms go around the galaxy's center. When spirals are tightly wound, the arms are almost round and have a low pitch angle. In Triangulum, that slope is much steeper, almost open-handed, like a dancer in the middle of a spin with their arms spread out. As a result, a galaxy that doesn't look like a helix but more like a pinwheel in space. That it's not tight tells us a lot about how stars are made. Unlike galaxies with defined bar-driven arm structure, M33 lacks a central bar, meaning the arms are likely shaped by local gravitational perturbations rather than a unified pattern. Essentially, it's star formation on shuffle mode. These arms don't flow out in even spirals. They branch, fork, and fade in places, making them appear patchy or even broken. Yet, those very patches are where new stars are being born in bursts of blue and ultraviolet brilliance. M33 has 3 main spiral arms, but they're not identical twins. The northern arm is brighter and more prominent, marked by strong emissions from star-forming regions like NGC 604. The southern arm, by contrast, is dimmer and more fragmented. Astronomers have traced these arms using everything from visible light images to hydrogen alpha emissions, and they've discovered something wild. Star formation isn't uniform. Instead, it pulses along the arms in pockets, almost like rhythmic sparks down a fuse. One reason why this isn't even. The arms of Triangulum don't have big waves of density compression like those in Andromeda or other grand design spirals. In those galaxies, spiral arms slow down gas and make it stick together to form stars, like traffic jams in space. But M33 doesn't have that kind of planned organization. Instead, you have gravity instabilities on a smaller scale. These are local events where cold gas is compressed and new stars are born in scattered bursts. To really understand how Triangulum's arms behave, scientists use something called Fourier decomposition. It's a mathematical method that breaks down the galaxy's light profile into patterns, identifying how symmetrical or lopsided the arms are. The result? Triangulum doesn't show the strong dominant modes of symmetry that define tightly wound spirals. Its structure is more diverse, more randomized, and arguably more beautiful in its irregularity. This flocculent nature also means Triangulum is incredibly helpful for testing star formation models. Without a strong bar or bulge, the cause and effect relationship between gas compression and star birth becomes easier to isolate. You can track where molecular clouds form, watch them collapse into stars, and trace the resulting feedback, like stellar winds and supernovae, without the complexity of a crowded core. Triangulum still turns like a clock, even with all this chaos going on. Its arms move in smooth curves that keep the stars in sync with the galaxy's flat spinning curve. The mix between chaos and order is what makes M33 a real gem in the field of astrophysics. Its patterns are hard to predict, but its speed is steady. This is a paradox that can only happen on a galactic scale. When viewed in different wavelengths, the arms reveal different faces. In radio and far infrared light, you'll see the cold gas and dust, raw materials waiting to ignite. In ultraviolet, you'll see the youngest, hottest stars blazing to life. In optical light, you catch the blended structure, the grand illusion of continuity made from millions of discrete bursts. This multi-wavelength portrait reveals the story of a galaxy in constant motion, creating and destroying stars in an endless loop. From Earth, Triangulum is seen at an angle, not perfectly face-on. This tilt adds a layer of depth to the spiral pattern, making some arms appear more prominent due to overlapping star fields. That's why astronomers use tools like Doppler shift and H-alpha velocity maps to decode the true motion of the arms, measuring not just what we see, but how it's moving in 3D space. It's kind of like jazz, really. Most spiral galaxies are like symphonies. They are tight, planned, and repeated. M33, on the other hand, is more like freestyle. Its circular shape doesn't stick to a strict score. Instead, it riffs and flows, led by feedback from other stars and slight gravity. That makes it more interesting to look into, but harder to model. NGC 604, the largest star factory in the local group. If you could go into one star-forming area in the whole local group and see the raw power of creation in all its glory, it would be NGC 604. This gigantic H2 area is tucked into one of Triangulum's spiral arms. It's not just big, it's ridiculously big. There are more than 1,500 light-years between it and the famous Orion Nebula. It looks like a nice neighborhood playground. A huge number of stars are born here, and ultraviolet light fills the space around them. Ionized gas glows like a flame in space. NGC 604 isn't a star cluster. It's more like a star-forming city, a sprawling complex of gas, radiation, and young, searingly hot stars packed into a single area. Inside this massive bubble of glowing hydrogen, over 200 massive stars have recently formed, many of them more than 20 times the mass of the Sun, and their radiation. It's powerful enough to carve cavities into the surrounding gas, creating a web of filaments, arcs, and shells that stretch across light years. What you're seeing in NGC 604 is the result of a feedback loop. It starts with a cold, dense cloud of hydrogen collapsing under its own gravity. As stars ignite, they blast out ultraviolet light and stellar winds, which then compress nearby gas and trigger even more star formation. It's like a domino effect of birth, where one stellar generation helps build the next, even as it reshapes the environment in violent ways. The gas inside NGC 604 isn't just bright, it's also moving. When winds from young stars hit each other at speeds faster than sound, they heat the gas and send shock waves through space. Some of this turbulence can be seen in X-ray and radio waves, which let scientists make maps of the hot plasma and magnetic bubbles that are made when blasts and star outflows meet. NGC 604 is a battleground for stars that are still growing up. One reason this region stands out is its relative lack of obscuring dust. While many star-forming regions are shrouded in darkness, NGC 604 is unusually exposed. That means telescopes, especially the Hubble and James Webb, can peer deep into its core and watch the process of stellar birth unfold in near real time. You can trace the life cycles of stars from their initial collapse to their emergence as full-blown giants radiating intense UV light. It's interesting how well planned this chaos looks from a distance. The charged gas makes a hole in the space, and young stars shine light into it. Where radiation meets colder gas on the edges, hydrogen alpha light shines, making a bright red rim that marks the region's edges like a galaxy's sunset. The pressure of growing gas is pushing these edges together, which is where new stars are most likely to form next. But NGC 604 isn't just a local spectacle. It's a Rosetta Stone for understanding how starbursts work in distant galaxies. Its size and structure are similar to giant H2 regions seen in galaxies millions of light-years away. By studying NGC 604 up close, astronomers can decode what's happening in those far-off systems. It's like having a life-sized model of cosmic evolution sitting just 2.7 million light-years from Earth. The lack of a single dominant star. Unlike the Orion Nebula, which is lit up by a few ultra-bright sources, NGC 604's energy comes from a dispersed population of massive stars. This suggests a different star formation mechanism, one that produces clusters of stars instead of centralized giants. That gives it a unique signature and raises questions about how environmental factors shape star formation on large scales. Spectroscopy shows more. Scientists can figure out what the gas is made of, how hot it is, and how fast it is moving by looking at the light it gives off. They found that NGC 604 has a slightly lower metallicity than our galaxy. Metallicity is a measure of how many elements are heavier than helium. This matches Triangulum's general chemical makeup and shows how galaxies change chemically over time. NGC 604 is just one of dozens of H2 regions scattered across M33, but it's by far the most dramatic. Its mass, energy, and structure make it a touchstone for understanding how galaxies like Triangulum build their stellar populations. It's a star factory, yes, but it's also a cosmic classroom, a place where theory meets observation and the laws of physics play out in the open sky. Massive blue giants, Triangulum's brightest beasts. Some stars do more than shine, they rule, and the most beautiful lights in the Triangulum Galaxy come from its huge blue giants. These stars are the powerhouses of the universe. They are dozens of times the mass of the Sun and are burning hot, fast, and furious. The stars in this picture would walk down a red carpet in Triangulum if it had one. Many of these stellar titans are found within NGC 604, but they also pop up throughout the galaxy's spiral arms. Their color tells the story first. These stars glow blue because they burn at incredibly high surface temperatures, upwards of 30,000 degrees Celsius. That's hot enough to unleash a flood of ultraviolet radiation that shapes the galaxy's structure, lights up ionized gas clouds, and helps trigger the birth of new stars. But don't be fooled by how pretty they are. The lives of these giants are short and violent. 10 billion years is a long time for a star like our Sun to burn. A blue giant? You're lucky to get 10 million. They're like stars from another world. They burn out young but have a huge effect before they die. Most of them die in spectacular supernova events that send shockwaves through the gas clouds around them and add heavy elements to the galaxy. So where exactly are they? Astronomers use spectroscopic surveys to track these giants across M33. By analyzing the light they emit, they can identify surface temperature, luminosity class, and chemical fingerprints. The brightest and hottest of these stars fall into the spectral type O and early B, some of the rarest and most energetic types of stars in the universe. Triangulum offers a special advantage in studying them. Because the galaxy is tilted just enough to give us a clean view of its disk, and because there's relatively little obscuring dust, researchers can identify individual stars even at this vast distance. Instruments like Hubble and the Very Large Telescope, VLT, have resolved blue supergiants across M33's arms, some with over 100,000 times the luminosity of the Sun. And these beasts are not just bright, they're also wind machines. Blue giants lose mass at an incredible rate, shedding their outer layers through powerful stellar winds. These winds can reach speeds of thousands of kilometers per second, carrying material into space and sculpting the galaxy's interstellar medium like a leaf blower on overdrive. That outflow not only affects the star's own evolution, it helps fuel the next generation of stars. It's crazy how quickly these huge animals go through the steps of life. They start out as thick molecular clouds, catch fire quickly, move into the main chain, and begin fusing hydrogen in their centers. But after a few million years, they get bigger and sometimes change into bright blue variables or even red supergiants. When they finally blow up, called core collapse supernovae, they leave behind neutron stars, black holes, or sometimes nothing at all. Some of the brightest known examples in M33 are so luminous they can be seen in low-resolution images of the galaxy itself. That's how dominant they are. Astronomers have identified clusters that contain multiple blue giants packed into tight regions. turning entire neighborhoods of space into glowing beacons of radiation. Their combined energy output changes more than just the gas in the area. It also helps control the formation of stars along the spiral arms. Too many giants forming at once can wipe out material that is making stars with their radiation and winds, stopping the process in that area. Blue giants are both makers and destroyers because, based on how many are nearby and how many are active, they can either fuel or stop the birth of new stars. Blue giants are also important for helping us figure out how galaxies other than M33 work. They are so bright that they can be used as standard candles, which are measured signals that help figure out how far away galaxies are that are millions of light years away. In this way, they're not only nice to look at, but also very important tools for measuring the distances between galaxies. From the point of view of art, they're just theatre. When scientists draw pictures of Triangulum, these stars make the pictures look good. Their fiery ferocity and scorching blue halos make raw science look like a work of art. Star-forming rings, a 10,000 light-year burst zone. Think of a circle of fire, but instead of flames, it's a ring 10,000 light-years wide made up of young stars, bright gas, and swirling dust. That is what the Triangulum Galaxy's heart is surrounded by. This wide band of very active stars is called a star-forming ring, and it goes around the center of the galaxy like a cosmic flare that never goes out. Along with being beautiful, it tells us a lot about how M33 makes stars in ways that are very different from how our own Milky Way does it. The ring itself lies roughly 10 kiloparsecs, or 32,000 light-years, from the galactic center. That may sound far, but in M33's relatively small disk, it places this ring close to the zone where spiral structure and rotational dynamics really start to dominate. It's not perfectly circular, and it's not always easy to detect in visible light, but in the ultraviolet and infrared spectrum, it pops like a neon sign in space. Astronomers have long debated why such a ring exists in the first place. In some galaxies, rings form as a result of resonance, essentially the inner orbital speed of stars, and gas lines up with certain natural frequencies in the galaxy's rotation. These resonant rings become dense, gather material, and ignite with new stars. But Triangulum has no major bar structure to drive this kind of resonance, which makes its ring a bit of a mystery. Something else must be at play. A gravitational reaction in the past is one option. In the past, millions of years ago, M33 may have passed close to Andromeda, making waves of instability in its disk. It's possible that those waves spread out, pushing gas into a loose ring and starting a long period of star formation. It's like a wave ripple in the cosmos, subtle, delayed, but very powerful. When we zoom into this ring with modern instruments like Galix in the ultraviolet and Spitzer in the infrared, we see it isn't smooth at all. Instead, it's made up of discrete star-forming knots, individual clusters and pockets where gas clouds have collapsed into stellar nurseries. Each one of these zones is a mini NGC 604 in its own right, filled with young, hot stars blowing ultraviolet radiation into the surrounding dust. This ring has become a popular place to study how the environment changes the birth of stars. The galaxy's outer arms are quieter, with more gas that is spread out and stars being born more slowly. But in the ring, the mass of the gas, the winds from the stars, the UV rays, and even the turbulence all go up, as if the whole area were stuck in a fast-paced loop of star formation, feedback, and growth again. It's also where some of Triangulum's most intriguing metallicity gradients are observed. The stars born closer to the center of the ring tend to have slightly higher metal content than those farther out. An expected result if the ring is gradually pushing material outward as new stars enrich the surrounding medium. This isn't just about making stars. It's about evolving the chemical recipe of the galaxy in real time. Perhaps the most striking thing about the star-forming ring is how cleanly it slices across M33's structure. It cuts across spiral arms, weaves through dust lanes, and shows up in nearly every wavelength we observe. It's as if this galaxy built a track around itself, a cosmic racetrack where gas gets funneled, compressed, and lit on fire by newborn stars. The ring is rich in cold molecular gas, the raw ingredient for starbirth. Observations using carbon monoxide, CO emissions, show that dense clouds gather along this ring like kindling around a fire pit. Where the gas reaches peak density, stars ignite. Where it remains too diffuse, the potential just sits there, waiting for a nudge. The ring is a great place to try galactic models because it has the right amount of potential and ignition. They can guess where the next wave of stars will appear by modeling how the gas moves along the ring. That's why the Triangulum star-forming ring is more than just a show. It's like a crystal ball that shows us what's going to happen next. What's the point of this ring? It proves that galaxies don't always form stars in swirls or bulges. They sometimes build highways of creation, which are long, curved paths, where the conditions are just right to light up the universe. This process is best shown in Triangulum's 10,000 light-year burst zone, which is part of our local group. The pulsing heart. What lies at M33's core? There is a terrible secret at the heart of most spiral galaxies, a giant black hole. As the saying goes, there is a gravity monster in the sky that is millions or even billions of times the mass of our Sun. It controls everything around it. However, Triangulum always doesn't want to follow the rules. At its core is a mystery that challenges explanation. There is no bulging center, no bright light, and maybe even no black hole at all. What is going on in the middle of M33 then? From a distance, M33's core appears underwhelming. It lacks the bright swollen nucleus seen in galaxies like the Milky Way or Andromeda. There's no clear bulge of old stars, no intense central starburst region, no swirling disk of gas like you'd expect near a massive gravity well. Instead, it's flat, subtle, deceptively quiet. But the truth is, there's more happening here than meets the eye. The central region of Triangulum spans only a few hundred parsecs and is surprisingly faint. It contains a tightly packed cluster of stars, but not a dense elliptical-shaped bulge. Spectroscopic surveys reveal a population of intermediate-age stars mixed with younger ones, a sign that the core isn't entirely dormant, just different. It's as if the heart of Triangulum skipped the standard galactic template and chose a minimalistic layout instead. Is there a black hole in the middle? In short, maybe. The long answer, it's not simple. Earlier research that used velocity dispersion readings, the speeds at which stars move around the center, suggested that if there is a black hole, it must be pretty small compared to other galaxies. Up to about 3,000 solar masses is the most that it can weigh. That's really small. The Milky Way's black hole, on the other hand, is about 4 million times the mass of the Sun. It's one of the few spiral galaxies with a decent size that appears to either lack a supermassive black hole entirely or host one that's barely past the intermediate mass stage. And that fact messes with a lot of assumptions in galactic astronomy. Because one of the most consistent rules in the cosmic playbook is the M-sigma relation. The idea that the mass of a galaxy's central black hole correlates with the velocity spread of stars in the bulge. No bulge, no black hole, or maybe just a very modest one. This has turned Triangulum's core into a scientific battleground, an arena where theories about black hole formation, galaxy mergers, and stellar dynamics are being tested. Some astrophysicists argue that M33 simply never accumulated enough material to form a central monster. Others think it once had one, but lost it during a collision or ejection event early in its life. And a few believe that it's still there, just hiding, too faint or too quiet to detect with current instruments. In 2012, NASA's Chandra X-ray Observatory took a hard look at M33's core, trying to pick up X-ray emissions, something a black hole might release as it devours nearby material. The result? Crickets. Nothing conclusive. If there is a black hole there, it's either not feeding or doing so at an absurdly low rate. It's like finding a tiger that hasn't hunted in years. You start to wonder if it's even in the jungle. The main star cluster does seem to be moving and rotating. That much we know. It's not static. It changes. There isn't a very bright core, but there is some UV activity, which could be related to the formation of low-level stars or compact remains like neutron stars. All of this points to one conclusion. M33's core is quiet, which is very useful for science. It may not be empty, though. This quietness makes Triangulum a rare control sample in a universe full of noisy centers. It lets astronomers study how a spiral galaxy functions without a dominant black hole influencing gas dynamics, feedback loops, and star formation near the center. That makes it more than an oddball. It makes it essential. Also, there's the big picture question. What does M33's lack of a center black hole mean for its slow but steady growth? Will it be eaten by Andromeda in a few billion years, at which point it will have one? Or is it proof that not all galaxies grow and change in the same way? Bach Globules, dark cradles of newborn stars. It's easy to get lost in the bright parts of Triangulum's galaxy, the blue giants that are on fire, the H2 regions that are burning, and the nebulae that are lit up like neon signs. But light isn't where the story of how stars form really begins. It starts out in the dark. There is silence at the beginning, and it starts with Bach globules, which are small, thick clouds that most people don't notice. These tiny, cold knots of gas and dust might not look like much. They appear as dark smudges against brighter backgrounds, cosmic blind spots that absorb more light than they emit. But inside those shadows, stars are quietly being born. Bach globules are some of the most efficient natural incubators in the universe, and M33 is full of them. Named after astronomer Bart Bach, who first proposed their role in stellar formation in the 1940s, these globules are compact, isolated, and extremely cold, often only a few dozen degrees above absolute zero. They're made mostly of molecular hydrogen, peppered with dust particles that scatter and block light from passing through. Their sizes range from a fraction of a light year to a few light years across. But what they lack in volume, they make up for in density. In Triangulum, Bach globules are found mostly along the spiral arms, and especially near active star-forming zones like NGC 604 and the massive star-forming ring. They often sit at the edges of brighter nebulae, nestled like seeds in a fruit. And like seeds, they're packed with potential. Inside, gravitational forces slowly collapse the dense gas, pulling material toward the center until the pressure becomes high enough to ignite nuclear fusion. That's how a star begins. It is famously hard to study these globules. Astronomers can't see inside them with visible light, so they use infrared and radio waves to look inside. Thanks to its strong infrared instruments, the James Webb Space Telescope has made it possible to see into the center of these dark clouds, where young stars are still wrapped in their dusty cocoons. Some Bach globules in M33 contain not just one protostar, but small clusters, mini-stellar families being born together. Others show evidence of outflows and jets, narrow beams of gas blasting outward as new stars fight to balance gravity and angular momentum. These aren't static voids. They're dynamic, active, and alive with motion you can't see with the naked eye. There's also evidence that external radiation, like from nearby blue giants, can trigger the collapse of a Bach globule. This process, called radiation-driven implosion, adds another layer of complexity. It means that star formation isn't just internal, it's collaborative. It's influenced by the neighborhood. One generation of stars can literally push the next into existence by lighting a fire under nearby gas clouds. The Bach globules in the Triangulum Galaxy act as a cosmic barrier or a point of change. One side has cold gas that doesn't have any shape. At the other end is a young star that is about to shine. Everything in between takes place in these tiny, cold areas, where physics rules take over and amazing things happen. And while they may not be flashy, Bach globules are essential to understanding the entire star-forming engine of M33. Without them, there are no stars. Without stars, there's no feedback, no metal enrichment, no planetary systems, no supernovae. They are the hidden catalysts behind every bright spectacle we've seen so far. The coolest part? They're still taking shape. Bach globules in Triangulum are slowly breaking as you read this. They are making the next generation of light that will one day shine across the sky. Those stars won't show up for a very long time, but they're on their way. Compact star-forming knots clusters born in chaos. The knots are where you'd feel M33's heart the most. These aren't the usual star groups that are properly lined up. They're messy, clumped together, and natural. These tight star-forming knots are spread out along Triangulum's spiral arms. They're like pressure points where the galaxy's gas gets squished together in crazy bursts of creation. They may be the most important parts of the star engine that aren't given enough credit. The way these knots are grouped together is what makes them stand out. These are areas that are only a few dozen light-years across and are full of thick clouds and newly formed stars. Some are packed full of thousands of young, huge stars that give off enough energy to ionize the gas around them and make tiny bubbles in the space between the stars. Others seem quieter at first glance, but they hide the early signs of stars that are still in their dusty birth cocoons. These clusters are often found along the most active parts of M33's spiral arms, particularly in places where density waves or turbulence has forced gas to bunch up into gravitational pressure points. They don't always sit at the center of beautiful, sweeping nebulae. Some are tucked into edges, stitched between dust lanes, or flaring up along otherwise dim and quiet parts of the galaxy. That randomness, it's part of the magic. In a single compact knot, you might find multiple generations of stars forming nearly side by side. This suggests a kind of feedback loop happening on a microscale. One group of stars ignites, its radiation pushes against nearby gas, and the compression sparks another round of collapse. It's a layered eruption, where stellar generations form like stacked firecrackers, each blast setting off the next. These knots also tend to have incredibly high star formation efficiency. That means more of the available gas actually becomes stars, as opposed to just floating around uselessly. In galaxies like Triangulum, where the overall environment is more diffuse compared to the Milky Way, these knots act like stellar accelerators, getting more bang per cloud than you'd expect. Astronomers turn to infrared and radio wavelengths, which can cut through the thick dust and reveal the heat signatures of protostars. Some of the most compact knots in M33 show signs of having formed entire open clusters that will, over millions of years, drift apart but remain chemically linked like cosmic siblings. In a sense, these tight knots are the origin stories of future constellations. There's also something unusually chaotic about how these knots evolve. Unlike larger nebulae or star-forming rings that show more uniform structure, these knots often fragment quickly. The gravity wells inside them are steep and jagged, causing material to collapse in clumps instead of smooth waves. That means fragmentation is faster, starbirth is more erratic, and the result is a chaotic tapestry of stars in every phase of formation. Bow shocks and stellar winds are all around many knots. These are signs that the biggest stars inside them are already starting to change the landscape. These winds can blow out holes, squeeze gas next to it, or even blow away the rest of the knot before it's fully formed. Part of what makes these places so interesting to study is the fine line between making stars and killing the environment. In M33, compact knots are also surprisingly resilient. Despite their small size, they often survive in the face of galactic rotation, shear forces, and feedback from nearby supernovae. This resilience suggests they're held together not just by gravity, but by high-density gas structures with magnetic support, another layer of complexity that's only just beginning to be understood. One reason why these knots are so important. They show what kinds of conditions were around when stars were first being formed in galaxies. In the beginning of time, galaxies were smaller, less organized, and less orderly, just like these areas. By studying them in a galaxy like M33 that is easy to get to, scientists can go back in time and see how the first stars and groups might have joined together at the beginning of time. These knots don't stay compact forever. Over time, the stars drift apart, the gas disperses, and what's left is a trail of stars that trace the history of a once intense region of creation. But for the brief window that they're active, these knots are everything. Birthplaces, battlegrounds, blueprints. H2 regions glowing gas clouds shaped by ultraviolet light. They are everywhere in Triangulum. They are huge, bright bubbles of hydrogen gas that look like light signs in a city in space. These are H2 regions where stars are born and become colorful, chaotic ball of light that makes M33 look like it's always exploding. But the way they glow isn't the only thing that makes them beautiful. That glow is caused by an unseen rush of ultraviolet radiation from new stars that changes the way the atoms around it are made. So what is an H2 region exactly? The name refers to ionized hydrogen atoms that have lost their lone electrons after being zapped by high-energy photons. These UV photons come from young, massive stars, typically O-type and early B-type behemoths that have recently formed inside dense clouds. When that light collides with the surrounding gas, it strips electrons from the hydrogen atoms and creates a cloud of free particles. As those electrons eventually recombine with protons, they release energy in the form of light, mostly in the red hydrogen alpha part of the spectrum, which gives these regions their signature glow. In Triangulum, these regions are everywhere, some huge, like NGC 604, and some just a few light years across. They're strung along the spiral arms like Christmas lights, tracing the locations of recent and ongoing star formation. And unlike diffuse nebulae that can hide in shadow, H2 regions scream for attention. They're visible in multiple wavelengths, from optical to radio to X-ray, and each view reveals a different layer of the drama playing out inside. Some H2 regions in M33 are isolated, like glowing islands in the sea of starlight. Others are tightly clustered, forming massive complexes that could one day evolve into entire star clusters or open associations. Regardless of size, their structure is anything but calm. These are violent, high-pressure environments filled with shocks, turbulence, and outflows. The newly formed stars inside them aren't gently warming their surroundings, they're blowing it apart. Think about the champagne flow effect. When UV light makes a bubble in a thick cloud of gas that grows, the pressure inside the bubble rises quickly. It finally breaks through the thinner parts of the cloud, letting the ionized gas leave in a steady stream, like popping the cork on a bottle of cosmic Prosecco. This process not only changes the structure of the area, but it also sets the stage for future star formation in the space around it. And H2 regions aren't just passive backdrops. They're active players in shaping the galaxy. Their expansion compresses nearby gas clouds, triggering the collapse that forms new stars. This domino effect means that one generation of stars can directly lead to the next, each glowing bubble a link in the ongoing chain of stellar creation across M33's disk. Astronomers use H2 regions as signposts. Because they're tied so tightly to young, massive stars, their distribution tells us where a galaxy is growing. In M33, they cluster along the spiral arms, but don't always follow a perfect pattern. Some sit at the edges of arms, or in slightly offset lanes, possibly due to past tidal interactions or spiral wave irregularities. This mismatch provides valuable clues about how gas flows and rotates inside the galaxy. H2 regions also serve as natural laboratories for understanding elemental chemistry. By analyzing the light they emit, astronomers can determine the abundance of elements like oxygen, nitrogen, and sulfur, key markers for a galaxy's chemical evolution. In Triangulum, these measurements show a gentle metallicity gradient, with more metal-rich gas near the center and leaner, more primordial gas at the outer edges. The threads and loops inside these areas may be the most interesting to look at. H2 regions are not flat blobs. They often have complex, fractal-like structures, such as thin strands of charged gas, bright edges along shock fronts, and dark dust globules that stand out against glowing clouds. These features give us a hint of how crazy things are inside. Competing flows, magnetic fields, and radiation pressure are all mixed up in a dance that is always changing. And despite their brilliance, H2 regions don't last long. Once the central stars age and stop emitting strong UV radiation, typically after just a few million years, the gas begins to cool, recombine, and fade. The region dissolves, leaving behind a loose cluster of stars and traces of the past in chemical and dust structures. Their glow is temporary, but their legacy is permanent. Cold molecular clouds, where stars begin their story. A star hides before it shines. It starts out in the coolest parts of the galaxy, in huge clouds of molecular gas that move through the spiral arms like sleeping giants. It is completely dark and quiet there. These clouds are the first part of the story of the stars in Triangulum. They're not smart, they don't shine, but that's where everything starts. Molecular clouds, also known as giant molecular clouds, GMCs, are made primarily of molecular hydrogen, H2, the simplest and most abundant molecule in the universe. But molecular hydrogen doesn't shine in visible light, which means we can't see these clouds directly. Instead, astronomers trace them using other molecules like carbon monoxide, CO, which emits a signature glow in radio wavelengths that gives away the location of the otherwise invisible hydrogen. Along the twisting arms of M33, these clouds form long bands that go on for hundreds of light years. It's cold. It's very cold. Temperatures are very low, usually between 10 and 20 Kelvin. Atoms move so slowly at these points that gravity has a chance to take over and pull matter inward until stars are born at the densest places. These clouds are like galactic storage units, packed with everything needed to build a star: hydrogen gas, helium, trace amounts of carbon, oxygen, and heavier elements, along with fine grains of dust. And because the temperatures are so low, these materials don't move much, allowing gravity to quietly concentrate them into cores, the seeds of future suns. Interesting thing about Triangulum is that it doesn't have as many big molecular clouds as galaxies like the Milky Way. However, the ones it does have are very good at making stars. Researchers using the IRAM 30-meter telescope and ALMA have made a map of M33's CO emissions. This map shows hundreds of cold clouds with different sizes and shapes. Some are thick, closely packed knots, while others are long and thin, like cotton stretched across the bones of the galaxy. What makes a molecular cloud collapse into stars? Several things. Sometimes it's internal turbulence, a kind of random churning motion that causes part of the cloud to compress. Other times it's external, a shock wave from a supernova, a passing spiral density wave, or radiation pressure from nearby stars. In M33, all of these triggers are in play, creating a galaxy-wide cascade of collapses and creations. When a part of a molecular cloud hits a certain density, it starts to fall apart because of its own weight. At first, this process is slow. It takes hundreds of thousands of years. But as mass gathers, it speeds up. At some point, the center's pressure and temperature will rise high enough to start hydrogen fusion. A star is born. These clouds are also shaped by what they create. As new stars form, especially massive ones, they send out powerful winds and radiation that begin to erode the cloud from within. This feedback sculpts the remaining gas into pillars, shells, and bubbles, some of the most iconic structures in astronomy. In a sense, stars dig their way out of their own birthplaces. In Triangulum, this feedback is especially visible. Many molecular clouds show signs of disruption: bright rims, evaporating edges, and embedded H2 regions that mark the sites where stars have just formed. These aren't gentle environments. They're volatile, changing rapidly over just a few million years. Even with all of this chaos, cold molecular clouds are incredibly stable over time. They move slowly through the sky for tens of millions of years, only becoming stars when something happens nearby. They keep a galaxy's growth in check by saving fuel until the right spark sets it on fire. What's also interesting is how these clouds help shape the structure of the galaxy itself. Their distribution along the spiral arms isn't random. It mirrors the gravitational and magnetic architecture of M33. And because CO emissions can be mapped so precisely, scientists use these clouds as tracers to understand the underlying rotation and mass distribution of the galaxy. Cold molecular clouds are calm and quiet at the same time. There is science going on inside them. Simple molecules are changing into more complicated ones. Organic molecules are made. Ice forms on dust grains. Some scientists think that these clouds might be where stars and the building blocks of life came from. Stellar nurseries, in transition, when star formation slows down. Not every area where stars are being formed is filled with light and energy. Some are slowly, quietly, and strangely going away. In Triangulum, some star nurseries that used to be very active are slowly going away. They aren't fully asleep yet, but something is shifting. The formation of stars is slowing down. It's getting less cloudy. The chaos is slowly dying down. This is the galactic twilight zone, where the fires of the universe start to cool down. It's easy to get mesmerized by the bright spots, glowing H2 regions, massive blue giants, and molecular clouds brimming with potential. But in between these highlights lie regions of transition. These are places where molecular gas still exists, but the density has dropped just enough that gravity can no longer collapse it into stars. The gas isn't hot, but it isn't cold enough either. It's stuck. Astronomers call these subcritical clouds, and they're like the embers of a burned-out fire, still present, still warm, but no longer raging. In M33, these clouds are scattered, especially around the outer edge of the inner disk and in between the spiral arms. They were once part of the great star-forming engine. Now, they whisper of decline. Why does this slowdown happen? The answer usually comes down to stellar feedback. When massive stars are born, they don't just light up, they fight back. Their ultraviolet radiation ionizes the surrounding gas. Their stellar winds blow open cavities, and their deaths as supernovae detonate shockwaves that scatter the remaining material. These processes can halt future star birth in the same cloud that created them. M33 gives us a living laboratory to study this. In several regions, you'll find young clusters adjacent to fading CO signals. The stars are there, but the gas that built them is vanishing. Over the course of a few million years, what was once a glowing, chaotic nursery becomes a shell of dust and trace molecules. Still visible, still moving, but functionally dead. There's also the loss of greenhouse gases in the climate. Triangulum doesn't have as much dust as the Milky Way or Andromeda because it is smaller. For its size, the rate at which it's making stars is pretty fast, but it's also using up its fuel faster. If the galaxy doesn't get a lot of new gas from collisions or cosmic strands, it might stop being able to make stars in the future. Some astronomers have begun mapping these fading regions as a kind of post-starburst terrain. By comparing infrared emission from warm dust with CO and H1 levels, they can track how long a region has been in decline. The results are surprising. Many of these zones only recently stopped forming stars, within the last few million years. In galactic terms, they're still warm to the touch. Even in these slowing zones, surprises emerge. A rogue cloud can collapse unexpectedly. A filament might sweep in and reignite activity. So these nurseries aren't completely dead. They're dormant, like fields in winter, waiting for spring or final decay. For Triangulum, it's important to understand these changes. It tells us not only where stars are forming, but also where they have formed in the past and might never form again. It helps scientists figure out what will happen to the galaxy in the future. For example, how long will it shine, and what kinds of stars will be most common when the gas runs out? Dust lanes, the dark highways of Triangulum. If a galaxy's stars are like fireworks, then its dust lanes are like its shadows. They are the dark threads that wind through M33 like veins in a leaf. You saw them, even if you didn't pay attention at first. They are the thin, almost scary lines that run through the spiral arms of the galaxy. They block out light and give the otherwise bright background of space some structure. But these aren't just nice touches for the eyes. These structures are real. They are roads of thick interstellar dust that shape everything from how stars form to what we can see of the galaxy. Dust lanes are made up of incredibly fine particles, tiny fragments of carbon, silicon, iron, and ices, each no bigger than a grain of smoke. But gathered in massive quantities, they become opaque. They block and scatter visible light, casting long shadows across the spiral arms. In Triangulum, these lanes are especially pronounced thanks to the galaxy's face-on orientation. We're looking almost directly down into its disk, and that gives us a front-row seat to the full web of interstellar architecture. You can't just leave these lanes there. As the galaxy spins, they move with it and follow its gravity curves. Often, they move close to the leading ends of spiral arms. Gas and dust build up in these places because of density waves, which are like traffic jams caused by gravity that squeeze things together. That compression doesn't just make shapes that can be seen, it also makes pressure, and pressure makes stars. Many of M33's most active star-forming regions are located right along these dark streaks. Dust lanes are often the outer wrapping of much larger molecular clouds, concealing the cold, dense regions where stars are about to form. In some places, they act like scaffolding, guiding how gas accumulates and where collapse begins. In others, they seem to thread through star-forming clusters like barbed wire, fragmenting the environment and feeding turbulence. They also help keep the galaxy's radiation budget in check. High-energy light, like UV and blue light, is absorbed by dust and then sent back out in the far infrared range. This helps keep molecular clouds from breaking apart due to radiation, and it also gives us another way to track action in the galaxy. The infrared light from instruments like Spitzer and Herschel has been used to map M33. What they see is amazing. The dust lanes light up like rivers of warmth running through the spiral structure. Some spiral arms have thick, well-defined lanes that stretch for hundreds of light years. Others are patchy, broken, or completely dust-free. This unevenness is a direct reflection of the galaxy's dynamic nature. Supernovae, stellar winds, and even the motion of the stars themselves disrupt and reshape these lanes constantly. In this way, dust lanes are both architects and artifacts, both shaping the future and holding evidence of the past. When you zoom in on one, you can see more details. There are small strands, knots, and threads wrapped up through the lane, like rope fibers. Some are so thick that they block out almost all of the stars in the background, making them look completely black against the glow of the galaxy. Others are more see-through, with bits of shade that show movement and structure just below the surface. These differences aren't just for looks. They indicate different stages of cloud evolution, from diffuse interstellar medium to prestellar core. Dust also plays a chemical role. The surfaces of dust grains are where many interstellar molecules form, including water, methane, ammonia, and complex organic compounds. These grains act like tiny chemical labs floating in space, enabling reactions that couldn't happen in the gas phase alone. In this sense, dust isn't just hiding star formation, it's helping fuel it on a molecular level. Of course, for astronomers, dust is both friend and foe. It helps map out the structure of M33, especially in the infrared. But in visible light, it's a nuisance, obscuring stars, distorting brightness measurements, and confusing attempts to gauge distance and composition. That's why mapping dust lanes accurately is so important. It helps correct observations across all wavelengths and build a clearer picture of the galaxy as a whole. The romantic part is that dust lanes only last for a short time. They move, they get thinner, they split up. Over many millions of years, the winds and radiation from the stars that are growing inside them will destroy them. The dark thread will break apart, leaving behind glowing groups and empty space. But new dust will gather in other places, being pulled into the circle like trash into a whirlpool. It will all start over again. Supernova remnants, shockwaves in the galactic disk. The sound of death is loud in Triangulum. There is no quiet fade into darkness. Instead, there is an explosion, a shockwave, a raw, unimaginable release of energy that can be heard through the spiral arms like thunder in a canyon. After these events, the space between the stars is scarred by twisted webs of hot gas, growing rings of debris, and glowing embers that light up the space between the stars. These are the remains of a supernova. They are all over M33. Supernova remnants, or SNRs, are what's left after a massive star explodes at the end of its life. The outer layers of the star are blasted outward at thousands of kilometers per second, slamming into the surrounding gas and dust with enough force to heat it to millions of degrees. That material glows in X-rays, radio waves, and sometimes visible light, depending on its temperature and density. What's left behind can be anything from a neutron star to a black hole, but the aftermath, that stays visible for tens of thousands of years. Triangulum is rich with these remnants. Astronomers have catalogued dozens of them across the disk of the galaxy using multi-wavelength imaging to track the footprints of stellar death. Some are big, stretching across 100 light-years or more. Others are compact and faint, fading into the background noise of the galaxy. But every one of them tells a story of a star that lived fast, burned bright, and died hard. G9831 is the name of one of the most well-known SNRs in M33. It is a beautiful structure that has been seen in both optical and X-ray light. It is a standard example of a shell-type relic, which is a roughly spherical structure with a bright edge around the edge where the shock front is crashing into the space between the stars. Plasma that is hot and has a low density glows in the middle. Over time it cools down. It's like seeing the splash of a cosmic stone being thrown into space. Some of these remnants are thermal, glowing from heat alone, while others are non-thermal, emitting synchrotron radiation from electrons spiraling around magnetic fields. The diversity of supernova remnants in M33 gives astronomers a lab to study all kinds of explosion outcomes, from single massive stars to binary systems that triggered type Ia supernovae by stealing mass from a companion. Supernovae are the universe's recycling plants. They forge elements heavier than iron in their final moments and scatter them into space, enriching the galaxy with oxygen, silicon, calcium, and more. Triangulum's SNRs are full of these signatures, heavy elements glowing in emission lines that let scientists trace how metals are distributed throughout the galaxy. The shock waves themselves are just as important. As they expand, they stir up the gas and dust in the galaxy's disk. They compress molecular clouds, trigger new waves of star formation, and create complex structures like filaments, arcs, and cavities. These are not isolated events, they're chain reactions. One supernova can set off another, carving vast regions of turbulence across hundreds of light-years. In M33, some remnants appear near dense star-forming zones, while others sit isolated in older, quieter parts of the disk. Their locations help map the stellar history of the galaxy, showing where bursts of massive stars formed, evolved, and ended their lives. They're also timestamps. By studying their size and expansion rate, astronomers can estimate how long ago the explosion happened, piecing together a timeline of death across the galaxy. Some supernova remains still have a neutron star or pulsar, which is the collapsed core of the original star. These pieces often glow in X-rays and gamma rays, flashing in a strange way that looks like lights in space. Some don't show any signs of a core, which suggests that a black hole formed instead. These are the giants' ghosts, floating through a galaxy that can't even remember their names. The great thing about SNRs in M33 is that they're not just old artifacts. In the galaxy, they are actively changing the scenery. They add energy to the space between the stars, which helps keep the pressure and chaos going. They make chemistry development possible. They even change the galaxy's magnetic field, bending it in new ways that send waves out into space that last for thousands of years. H1. Mapping, tracing hydrogen across the disk. For now, forget about the show of stars forming. Don't worry about the ultraviolet brightness and explosion excitement. Hydrogen, which flows quietly across the whole sky, is much more basic than all of that. Not when it's hot and full of ions. Not yet joined together to form stars. Just H1, which is cold and neutral hydrogen. And this is where you start to understand the bones of Triangulum. H1 is the most abundant form of hydrogen in the universe. Each atom consists of just one proton and one electron. It doesn't emit visible light, but it does release a specific signal at radio wavelengths, the famous 21 centimeter line. It's faint, but unmistakable. And thanks to that signal, astronomers can track this invisible gas across entire galaxies, including M33. The H1 distribution in Triangulum is nothing short of stunning. When astronomers map it, they reveal a spiral skeleton stretching well beyond the visible boundaries of the galaxy. While the starlight fades at the edge of the optical disk, H1 keeps going. Further, thinner, more diffuse, but still there. It outlines not just where the galaxy is, but where it could grow. Triangulum's H1 disk extends to more than twice the radius of its stellar disk. That's a big deal. It means the galaxy is sitting on a massive reservoir of raw material, primordial fuel that can be compressed into molecular clouds and then into stars. It also means that the spiral arms are more than just stellar arrangements. They're pressure waves moving through this invisible ocean of hydrogen. H1 tells us how the galaxy rotates. By measuring the Doppler shift of the 21 centimeter line across different parts of the galaxy, scientists can construct a velocity map. That's how we know that M33 has a flat rotation curve. Stars and gas at the outskirts orbit at nearly the same speed as those closer to the center. That defies Newtonian expectations unless something unseen, like dark matter, is providing the extra gravitational glue. So, in essence, H1 mapping isn't just about hydrogen. It's about proving that dark matter exists. But the gas itself has a lot of shape. It's not spread out like mist. It forms a huge web of pressure zones and gaps by clumping, arcing, and filamenting. Some areas look like they are being squished by spiral density waves, while others look like they are being messed up by supernova feedback or turbulence from new stars forming nearby. It is possible to see H1 holes in high-resolution scans. These are places where growing shells of gas have been blown away, most likely by the collapse of massive stars. In M33, H1 isn't just a passive background. It's an active participant in galactic life. It flows inward in some regions, possibly as part of gas accretion from the intergalactic medium. It cycles through the disk as part of the galactic fountain, ejected by stellar winds and supernovae, then cooled and pulled back in by gravity. This circulation keeps the galaxy alive, breathing gas in and out like a living system. Triangulum shows some signs of warping in its H1 disk. The outer edges tilt slightly out of alignment with the inner plane, possibly the result of gravitational interactions with nearby dwarf galaxies, or even past encounters with Andromeda. These subtle distortions are invisible in optical light, but stand out clearly in H1 velocity maps. The turbulence within the H1 layer affects how and where molecular clouds can form. It sets the stage for star formation by determining the pressure, temperature, and density of the gas. Without this cold, neutral hydrogen flowing through the disk, none of the structures we've talked about, H, two regions, star clusters, supernova remnants, could even exist. Because it is neutral, H1 is a very good marker. A lot of the things that change other gas stages don't change this one. It doesn't glow unless it's excited, and close stars don't ionize it unless things are really bad. So it's a starting point, a way to keep things under control in a world full of chaos. In M33, we've used H1 to reveal the full extent of the galaxy, to chart its motion, and to find hidden arms and extensions that would be invisible in starlight. It's like turning on a blacklight in a dark room. Suddenly, everything that was invisible glows with meaning. Open clusters loose families of young stars. There are close-together star factories and lone giants that light up the spiral arms in the Triangulum Galaxy's big star towns. But open groups, which are more social and more transitional, are in the middle. These are the open, sparkling groups of stars that were born together and traveled together for millions of years before slowly moving apart. and they are all over M33, following the pattern of new stars forming like breadcrumbs on a circular staircase. Open clusters form when a giant molecular cloud collapses and fragments into many stars at once. These stars, often numbering in the hundreds, are gravitationally bound, at least temporarily. They emerge together in the same neighborhood, sharing similar ages, chemical compositions, and even motion. But unlike their denser cousins, the globular clusters, open clusters are not forever. They're fragile, and in cosmic time, they're short-lived. In Triangulum, open clusters are particularly important because of the galaxy's relatively low stellar crowding. This makes it easier for astronomers to pick them out from the background population. Surveys using instruments like Hubble, Subaru, and Galex have catalogued hundreds of these clusters, from fresh blue-white groups only a few million years old to more faded red-tinged ones nearing the end of their unity. Open clusters are very important because they show how stars are being formed. Astronomers can figure out where and when stars were formed across M33's disk by looking at how they are spread out. It makes sense that many of them are found along the spiral arms, especially near thick H2 regions or molecular cloud complexes, since these are the places where stars give birth. Some groups, on the other hand, are surprisingly spread out. They are found in areas with less activity, which makes us wonder how far young stars can move from where they were born or how rough their birth clouds really were. The youngest open clusters in M33 often include massive stars, O and B types, that blast their surroundings with ultraviolet radiation. These luminous members burn out fast, sometimes in just a few million years. But their lower mass siblings, the G, K, and M-type stars, will live much longer, gradually dispersing into the wider galactic field. Over time, gravity from nearby stars, gas clouds, and the galaxy's overall tidal forces pull the clusters apart. What remains is a trail of related stars spread across the galaxy, cosmic cousins with shared DNA but no common address. Researchers really like open groups in Triangulum because they help them figure out what is right. Because it's pretty easy to figure out how old these groups are, usually by looking at their color and brightness. They can be used to figure out how stars have changed over time. You can see how stars with different masses change over time, including how fast they spin down, how their chemistry changes, and how the fact that they are binary makes them grow. They also help refine the galaxy's chemical enrichment timeline. Since clusters form from localized pockets of gas, their metallicity, the abundance of elements heavier than helium, reflects the composition of their environment at the time of birth. When astronomers compare metallicity across open clusters of different ages and locations in M33, they're essentially reading a chemical diary of the galaxy's past. In optical and ultraviolet images of M33, they show up as glittering beacons, tiny concentrations of light that sparkle against the smoother background of field stars. Some are still embedded in faint nebulae, their hot young stars ionizing the last remnants of the cloud that birthed them. Others are more diffuse, like a scatter of diamonds tossed into space, quietly aging in orbit around the galactic core. Also, M33 might be home to some giant open clusters, which would make the difference between normal open clusters and small globulars less clear. These thick groups could be leftovers from starbursts in the past, or the result of clouds that are incredibly big. Their presence shows that there is a range, even within the term open cluster, from weak swarms to almost eternal groups. Cepheid variables, Triangulum's natural timekeepers. It would pulse instead of tick if Triangulum had a clock. It was slow, steady, and wonderful. That's what traits of Cepheid do. These rare stars that pulse are more than just pretty. They rule the universe, using sticks to measure the universe. They're also useful in M33. They're important. We might not even know where Triangulum is without them. There is a group of stars called Cepheid variables that grow and shrink in a steady pattern, getting brighter and darker at regular times. The star is brighter when its rotation time is longer. Henrietta Swan Leavitt found this link between time and brightness at the beginning of the 20th century. It changed the field of astronomy forever. You can figure out how far away a Cepheid is by comparing how bright it looks from Earth to how bright it should be. Don't guess, just numbers. Triangulum is one of the key galaxies used to calibrate this method. Thanks to its relatively close proximity, around 2.7 million light-years, and its face-on orientation, astronomers have been able to identify and monitor dozens of Cepheids scattered across its disk. Some are nestled in young star-forming regions, others drift alone, glowing like cosmic metronomes in the darkness. The periods of these stars can range from a few days to several weeks, and their brightness can vary by more than a full magnitude. That's not just an observational curiosity. It's a key to understanding both the structure of M33 and the scale of the universe beyond it. It was observations of Cepheid variables in Triangulum, made with the Hubble Space Telescope, that helped refine the value of the Hubble constant, the rate at which the universe is expanding. These stars act like stepping stones on the cosmic distance ladder, helping us leap from the nearby universe to the farthest reaches of space with confidence. They're stars in transition. Most began their lives as massive main-sequence stars and are now crossing the instability strip of the Hertzsprung-Russell diagram, a region where stars become unstable and begin to pulsate. Their outer layers swell and contract in a battle between gravity and pressure, a cycle that repeats endlessly until they settle into a new stage or collapse entirely. The Cepheids in Triangulum tell us more than just how far away something is. They also tell us about the past. Most of these stars are only 10 to 300 million years old, which is pretty young. The places where they are found show where new stars have formed recently, and their metallicity, how much stronger elements they contain, tells us about how the chemicals in different parts of the galaxy have changed over time. Because Cepheids are so bright, they can be seen across vast distances even when embedded in dusty regions. That makes them perfect for mapping structure in a galaxy like M33. Astronomers can use them to trace the contours of spiral arms, the warp of the disk, and even subtle motions of the galaxy's rotation. Triangulum has also been the site of one of the most thorough studies of Cepheids ever done. Astronomers have made a very accurate list of these variable stars by using tools on both ground-based cameras and the Hubble Space Telescope. They have measured not only their light curves, but also their color, mass, and position in relation to other groups of stars. They're so beautiful that it rhymes. These are living stars that move, that blink in the big picture of time. They show us that stars aren't fixed. They change, move, and beat to a beat. We can measure the universe with that beat, which is pretty cool. Spiral density waves, the blueprint behind star formation. Some of the most beautiful things in the universe are spiral galaxies, which have graceful arms that spiral outward from bright galactic cores like frozen whirlpools of gas and stars. But those arms aren't made up of the same stars moving together in a circle. They are actually patterns, or waves, moving across the galactic disk like slow-moving traffic jams. These are waves of spiral density. In the Triangulum Galaxy, they're the quiet ones who plan most of the things that happen. Think of them as pressure waves moving through a flat disk of stars and gas. As the wave moves through the galaxy, it temporarily slows down material, compressing gas, bunching up stars, and setting the stage for star formation. It's not unlike how a ripple passes through a crowd of people. The individuals keep walking, but the wave of motion spreads through them. In the same way, stars orbit around the center of the galaxy, but the spiral pattern, created by the density wave, moves through them. In M33, this concept plays out on a nearly textbook level. While Triangulum lacks the strong, well-defined bar structure of some larger spiral galaxies, like the Milky Way or Andromeda, it still exhibits beautiful, loosely wound spiral arms. These arms aren't static. They're the visible result of spiral density waves sweeping through the disk and compressing gas into glowing lanes of starbirth. The key players in this process are gravity and differential rotation. Triangulum, like most spiral galaxies, doesn't rotate like a solid wheel. The inner parts spin faster than the outer parts. This differential motion naturally winds up any feature, and without a stabilizing mechanism, the spiral arms would quickly blur into chaos. But spiral density waves provide that mechanism. They maintain coherent arm structures over hundreds of millions of years by propagating as long-lived wave patterns in the disk. When gas rushes into one of these arms, it moves a little more slowly because the area is denser. While there is that pause, the gas builds up, which creates pressure. When the conditions are right, that pressure causes gravity collapse, which starts the process of being born of stars. It's a chain of events that spans the galaxy. Gas goes into a wave. It is squished. Stars are made. The stars then move away from the arm, leaving a line of bright new stars behind them. This is why star-forming regions in M33 often appear just downstream from the densest part of the spiral arm. By comparing the positions of molecular clouds, H2 regions and young open clusters across the arms of Triangulum, astronomers can actually see the time lag between gas compression and star birth play out in real spatial terms. The spiral pattern in Triangulum is interesting because it is a flocculent type. This means that its arms are not as smooth and even as the grand design spirals found in galaxies like M51. It's still possible for the spiral density wave process to be at work, though. It only means that local instability and star formation that keeps going on its own have a bigger impact on the structure that we can see. Still, there is proof of large-scale density waves, and their effect on M33's dynamics is deeply ingrained. Astronomers think that Triangulum's density waves may have been caused or made stronger by interactions with nearby galaxies, such as Andromeda. When these things happen, their gravitational pulls can create or strengthen wave patterns that last for a long time after the event. In models, even a short flyby can start spiral structures that last a long time in galaxies that wouldn't normally have them, like Triangulum. Spiral density waves affect more than just gas, which is another interesting fact. They change stars too. Stellar orbits can change slightly in places with a lot of stars, leaving behind small kinematic traces that scientists can measure. These movements help figure out the galaxy's gravitational pull and show where the mass is distributed that is hidden from view by the light. And perhaps most importantly, spiral density waves give us a framework to understand the structure of galactic evolution. Without them, star formation would be far more chaotic and less efficient. With them, galaxies like M33 can organize their gas into stable, recurring zones of activity. It's like turning random rainfall into an irrigation system, structured, predictable, and productive. The idea that these arms are waves and not fixed objects changes how we think about galaxies too. We didn't see those bright stars in an arm yesterday, and we won't see them again tomorrow either. The routine stays the same, but the people who are involved are always changing. One of nature's biggest tricks is that rigidity can be made from motion. Wolf-Rayet stars, the fading roar of massive winds. They scream as well as shine. Some of the loudest voices in the sky are Wolf-Rayet stars. It's not that they're bright, but what they do to the area around them. These are the last, most violent stages of some of the universe's biggest stars. Even though M33 isn't as big as the Milky Way or as violent as Andromeda, it has a lot of Wolf-Rayet stars that are burning through its arms like flames. So what exactly is a Wolf-Rayet star? It's a massive star nearing the end of its life, stripped of its outer hydrogen layers and now fusing helium or even heavier elements in its core. These stars were once O-type giants, but they've evolved into something more raw and exposed. And because they've shed their outer shells, they burn hotter, emit more ultraviolet radiation, and blow out powerful stellar winds at speeds exceeding 2,000 kilometers per second. These stars aren't spread out evenly in Triangulum. They tend to gather in places where new stars are being made, especially near stellar groups and nebulae, like NGC 604. They are the older children of great nurseries, the big ones that grew up too quickly and are now squeezing every last second. A lot of them don't make it past a few million years, but in their short time here, they add drama to the galaxy. Wolf-Rayet stars lose mass at rates up to 1 billion times greater than our Sun. That material doesn't just vanish, it collides with the surrounding interstellar medium, creating bow shocks, wind-blown bubbles, and feedback loops that disrupt and reshape entire regions of space. These winds clear out cavities, trigger new waves of collapse in nearby clouds, and fill the area with high-energy particles and radiation. In images of M33, the presence of Wolf-Rayet stars often aligns with glowing gas arcs, hollowed shells, and bright X-ray emissions. Their impact is visible, measurable, and violent. They act as accelerants in the chemical and physical evolution of the galaxy. But it's not just about destruction, it's also about legacy. Wolf-Rayet stars are thought to be progenitors of type Ib and type Ic supernovae, and possibly long-duration gamma-ray bursts. That means when they finally explode, they do so with style. And when that happens in Triangulum, the effects ripple far beyond a single region. These explosions enrich the interstellar medium with metals, carbon, oxygen, neon, feeding future generations of stars and planets. There are different types of Wolf-Rayet stars, classified based on their spectra. WN types show strong nitrogen lines, WC types show carbon, and the rare WO types show oxygen. M33's catalogue includes examples of WN and WC types, with their numbers helping researchers understand the galaxy's stellar population, its metallicity, and its evolutionary track. The ratios of WN to WC stars can even tell us about past starburst activity and how rapidly the galaxy has converted gas into stars. Triangulum is a great place to study these stars because, compared to the Milky Way, it doesn't have as much metal in it. This changes how stars evolve. Stellar winds are weaker in places with less metal, which lets massive stars keep more of their mass. This changes how they grow into Wolf-Rayet stages. When scientists look at the Wolf-Rayet groups in M33 and compare them to those in our galaxy and others, they learn more about how stars act in different cosmic situations. Wolf-Rayet stars have a unique visual signature. Their spectra show broad emission lines, and their color leans heavily toward the blue and ultraviolet. They're hard to photograph directly, but their influence is undeniable. They carve glowing rings in space. They power some of the brightest nebulae in the galaxy. They live fast, burn everything around them, and die young. There are only a few hundred Wolf-Rayet stars in M33 out of a total of tens of billions. However, they have too much power. They light up more than just the sky. They change its form. When we look at them, we see a cosmic event happening, a star tearing itself apart in a dramatic, beautiful, and short way. Neutron stars and pulsars, cosmic lighthouses of M33. Aside from black holes, they are the densest things in the Triangulum Galaxy, and they don't just sit there. They pulse, spin, and shoot. Neutron stars are formed from the remains of supernova blasts. Pulsars are neutron stars that spin very quickly and send focused radio or X-ray waves through space. In M33, these strange remains shine like lights in the dark, each one telling the story of a huge star that died but didn't go away. A neutron star forms when a star at least 8 times the mass of the Sun explodes in a supernova, ejecting its outer layers in a dramatic blast. What remains is the core, compressed down to the size of a city, maybe 20 kilometers across, yet with more mass than the Sun. The density is absurd. A sugar cube-sized chunk of neutron star material would outweigh Mount Everest. Triangulum has a lot of places where stars can form. In other words, it has plenty of great death. And where big stars have died, neutron stars are likely to stay. But it's hard to find them. Nebulae and bright stars give off a lot of visible light, but neutron stars give off very little. Instead, they usually show themselves by giving off radio waves, X-rays, or gamma rays, especially when they're pulsars that are spinning. Pulsars are neutron stars with strong magnetic fields tilted relative to their spin axis. As they spin, sometimes dozens or even hundreds of times per second, they emit beams of electromagnetic radiation that sweep across space like the rotating beams of a lighthouse. If Earth happens to lie in the path of one of those beams, we detect a rhythmic signal. Pulse, pulse, pulse. M33 is close enough, about 2.73 million light-years, for our telescopes to pick up some of these signals. Not many, but a few. And even a few are worth gold in galactic terms. The pulsars found in Triangulum help astronomers estimate the galaxy's rate of past supernovae. Each one is a fossil clock, ticking since the death of its parent star. For example, an X-ray pattern rather than radio waves showed up one pulsar in M33. These high-energy signs tell us that it's probably taking in matter, maybe from a binary partner. This brings up another part neutron stars play in Triangulum's story. They are part of strange twin systems. Some neutron stars move very close to other stars and steal gas that swirls down to their surfaces. As that gas falls, it gives off huge amounts of energy, which can cause short, powerful flares. These X-ray binaries are some of the brightest non-supernova sources in Triangulum. They show up vividly in space-based observatories like Chandra and XMM Newton, which have scanned M33 for years. By mapping these X-ray beacons, scientists learn not just where neutron stars are, but also how they behave under extreme conditions. Magnetic fields a trillion times stronger than Earth's. Gravity so intense not even atoms can remain intact. A second type of science tool in M33 is the pulsar. They can be used to measure conditions between stars because their pulses are so regular. Some are as accurate as atomic clocks. One way to tell how much gas is between us and them is by how their signals arrive slightly later at different wavelengths. That makes it easier to make a 3D picture of the space between galaxies. And just like in the Milky Way, pulsars in Triangulum may one day be used in pulsar timing arrays, which are networks of neutron stars that are perfectly timed to pick up gravity waves as they pass. Imagine being able to feel ripples in space-time by using dead stars in a different galaxy. It's the kind of writing about space that makes science seem magical. Neutron stars pack a lot of power for how small they are. Each one is a memorial to great rage and strength. They're not bright like other stars. They don't move around like gas clouds do. They are at the edge of life and death, flashing in time with the stars and carrying the secrets of the past of their galaxy. Magnetic fields, invisible lines that shape a galaxy. They're all around us, but we can't see them directly. Magnetic fields build galaxies without being seen. Their paths take them through spiral arms, around gas clouds, and even through the motion of space dust. They may not be visible in the Triangulum Galaxy, M33, but they have a big impact there. When scientists have the right tools, they can peel back the layers to see the structure that is hidden beneath the stars. The magnetic field in a galaxy like M33 is typically organized along its spiral arms. Think of them like unseen scaffolding threading through the disk. These fields are generated and maintained by a dynamo effect, a process in which the movement of ionized gas in the galaxy generates a large-scale magnetic structure. And in M33, this magnetic architecture aligns astonishingly well with the visible spiral arms we see in optical and radio images. But how do we even know these fields are there? We can't photograph them, but we can detect their fingerprints. One of the most powerful tools is radio polarization. When radio waves pass through a magnetized plasma, their electric field vectors twist, a phenomenon known as Faraday rotation. By measuring this twist, astronomers can determine the strength and orientation of the magnetic fields they've passed through. Polarization maps created by radio telescopes like the Very Large Array, VLA, have revealed coherent magnetic structures stretching thousands of light years. The field isn't uniform, though. It varies in strength and direction depending on the density of gas and the dynamics of nearby star formation. Stronger fields are often associated with regions of high turbulence, like where supernova remnants collide with molecular clouds. But magnetic fields aren't just passive threads. They actively influence star formation. In dense gas clouds, magnetic fields can either support a region, preventing collapse, or guide it, channeling matter into filaments that become the birthplaces of stars. In M33, some of the star-forming regions along the arms seem to align with magnetic ridges, suggesting that these invisible forces are shaping where and how stars are born. They also act as cosmic highways for charged particles. Electrons and protons ejected from stars and supernova follow these magnetic lines, spiraling around them as they move through the galaxy. These cosmic rays, in turn, interact with gas and dust, heating them and influencing their chemistry. In a very real sense, the magnetic fields mediate the dialogue between dead stars and newborn ones. M33's magnetic field appears relatively ordered compared to more chaotic galaxies. This suggests that its rotation is smooth and its dynamo engine stable. It's not just spinning stars and gas, it's winding up invisible energy into structured loops. These fields could even extend beyond the visible edge of the disk, forming magnetic halos that act as a protective bubble around the galaxy. People also have ideas about how these forces might affect the development of the galaxy over billions of years. As M33 moves through the local group and interacts gravitationally with Andromeda and, to a lesser extent, the Milky Way, those cosmic tides may slightly change or stretch its magnetic structure. Galaxies may connect with magnetic bridges and flaws that connect and weave their fates together in ways we are only starting to understand. The effect is real, even on a small level. When planets are grouped together, magnetic fields help impact disks grow. Sun flares and stellar winds are caused by them. They also add just the right amount of pressure to galaxies like M33, so that collapse happens more quickly in some places and more slowly in others. The galaxy would not only look different without them, it would also act differently. Cosmic rays charged particles racing through space. They're not visible, they're not there. However, very fast particles with a lot of energy are hitting the Triangulum Galaxy and even speeding away from it every second. In M33, these are cosmic rays, and they're not just guests, they are a part of the environment. It is fast, silent, and formed by forces that no one can see. Cosmic rays are charged particles, mostly protons, with some electrons and atomic nuclei, traveling at nearly the speed of light. Many of them come from supernova explosions, where shock waves accelerate matter to extreme velocities. Some originate from the Sun, others from distant galaxies, but many are homegrown, forged right in the arms of Triangulum. Every time a massive star dies, it blasts material into the surrounding space. That shock front can energize particles like a giant natural particle accelerator, slinging them outward through the galaxy. Triangulum's rich history of star formation and supernova events makes it a prime source of cosmic rays. But these rays don't just fly in straight lines. They spiral, bounce, and zigzag, trapped and guided by the galaxy's magnetic fields. That's where the invisible architecture of M33 comes back into play. Magnetic field lines don't just define structure, they shape motion. Cosmic rays follow these lines like race cars on invisible tracks, arcing through the arms, through the halo, and even beyond the edges of the disk. Cosmic rays make secondary particles and gamma rays when they hit atoms in the interstellar medium, mostly hydrogen and helium. Atoms can lose their electrons in these high-energy interactions, which can also start chemical processes and heat cold clouds that would otherwise turn into stars. In other words, cosmic rays don't just bring bad news, they also keep life in balance. It is one of the few galaxies that is close enough for scientists to study these effects as they happen. Radio antennas pick up the synchrotron radiation that cosmic ray electrons give off as they spin along magnetic fields. You can use these weak signs to figure out where cosmic rays are coming from and how strong the magnetic fields are in that area. The most energetic exchanges can be directly found with the help of gamma-ray detectors like Fermi. There's a kind of cosmic weather happening in M33, and cosmic rays are the solar wind of the galaxy, continuously bombarding its clouds and stars. Some even escape into intergalactic space, carrying with them the fingerprint of their origin. These outbound rays could be intercepted by spacecraft in our own system, giving us insight into the distant physics of another galaxy. But not all cosmic rays are born equal. Some of the most energetic ones may be connected to more exotic events, like pulsars, black hole accretion disks, or even interactions in galactic centers. M33's relatively calm core doesn't host a supermassive black hole as active as the Milky Way or Andromeda, but it's still producing enough energy through star formation and supernovae to generate a continuous stream of these particles. Cosmic rays may also play a role in regulating the flow of gas into and out of the galaxy. The pressure from cosmic rays can push back on inflowing gas, preventing it from forming stars too quickly. Over long timescales, this feedback loop helps balance growth and stability in galaxies like Triangulum. Cosmic rays affect nearly everything, from the glow of a nebula to the chemistry of a disk where planets are being formed. They are very small and hard to track, and each time something goes through, it leaves a mark, a wave, a trail, a change in temperature or energy. Rotation curve mysteries, the hunt for dark matter. Triangulum looks like a good galaxy at first glance. The spiral arms are tight and beautiful, and the star formation is busy but not crazy. It spins in a straight line around its own center, like a space wheel. But there's a problem that makes us question everything we thought we knew about mass and gravity. Astronomers didn't understand M33's spin graph when they drew it. It was way too fast for the stars to move. In a typical spiral galaxy, you'd expect the rotation speed of stars to drop off as you move farther from the center. Just like planets in our solar system orbit slower the farther they are from the sun. That's what Newtonian physics predicts, and that's what gravity should enforce. But that's not what we see in Triangulum, not even close. The stars in M33's outer arms keep spinning at nearly the same speed as those much closer to the core. This isn't just weird, it's impossible under the laws of visible matter. The outer regions of the galaxy don't contain enough stars or gas to produce the gravity required to hold those stars in place. If you only count what we can see, M33 should be flying apart. It's not though, it's steady, it makes sense. That means there's something else, a big thing, holding everything together. This is where dark matter comes in. Current models say that galaxies like Triangulum are surrounded by huge rings of unseen matter. This matter could be made up of particles that interact with gravity, but not light. These halos of dark matter give the flat rotating curves the missing mass they need to make sense. M33's rotation curve was one of the clearest early pieces of evidence for this phenomenon. Observations using 21 centimeter radio waves, ideal for tracking neutral hydrogen gas far out in the galactic disk, showed that the speed of rotation remained steady well past the edge of the visible stars. It was as if an invisible scaffold extended far beyond the luminous spiral arms, keeping everything spinning in sync. But while the rotation curve matches the dark matter model, the details still raise questions. For instance, does Triangulum's dark matter halo extend farther than its nearest gas clouds? Is it shaped like a sphere or a flattened ellipsoid? Is the dark matter smoothly distributed, or does it clump in strange patterns? These are not trivial questions. They touch the frontier of astrophysics. New computer models show that M33's halo might not be totally separate either. Because it is gravitationally tied to Andromeda, M31, some models say that their dark matter halos might be interacting or even crossing over. In this case, Triangulum's spin curve may show more than just its own shape. It might be slightly affected by the gravity dance of a much bigger neighbor. And this opens the door to even more speculation. Could tidal interactions between M33 and Andromeda have disturbed the dark matter halo? Are there subhalos, smaller clumps of dark matter, swimming within M33's larger one? Could these affect local star formation or even trigger asymmetries in the galaxy's spiral pattern? The galaxy we can see is only part of the story. The stars and gas we see are following the shapes of an unseen framework, which is held together by gravity but can only be seen when things are moving. In Triangulum, That structure goes much further than what any viewer can see directly. For the most part, the galaxy is moving too fast to be safe. One of the strongest quiet cases for dark matter in our galaxy is that it's not breaking apart. Tidal streams trails from galactic cannibalism. Galaxies don't just float around in space without doing anything. They push against each other, pull and eat each other. There is a cosmic eating frenzy going on, and Triangulum has its own dirty laundry in the galaxy closet. One of the most convincing pieces of proof. Streams of water, smaller galaxies that got too close and didn't make it out, left behind these faint, looping paths of stars. Tidal streams are like the ghost trails of past mergers. When a dwarf galaxy strays too close to a larger one, like M33, it gets stretched and torn apart by tidal forces. The gravity of the main galaxy rips stars from the smaller one and drapes them across space in long, curved lines. Over time, these streams can wrap around the host galaxy in spirals, arcs, or even rings, barely visible, but incredibly telling. For decades, astronomers suspected that Triangulum might have swallowed a few smaller galaxies in its past. But it's only in recent years, thanks to deep sky imaging and precision photometry, that they've started to spot the evidence. Faint overdensities of stars in the outer halo of M33 don't match the galaxy's expected smooth structure. Some of these clumps appear stretched, aligned along strange paths, or orbiting far beyond the main disk. All signs of tidal disruption. Possible stream that wraps around the edges of M33 like a loose band could be the pieces of a dwarf galaxy that broke apart a few billion years ago. The stars in this group don't move along the flat surface of Triangulum's circular ring. Instead, they move at strange angles, which points to a completely different beginning. And the best part? Some of them are older and have fewer metals than the local M33 population, which is another sign that they came from somewhere else. But tidal streams don't just tell a story of the past, they shape the present. As these disrupted dwarfs merge into M33, they inject fresh gas, stir up gravitational chaos, and possibly even trigger new waves of star formation. The infall of smaller galaxies may be part of why Triangulum has remained so actively star-forming compared to other spirals of its size. These streams are also very important for making maps of the dark matter ring around M33. The underlying gravity controls how stars move along a tidal stream. This means that the stars essentially follow the shape and density of the dark matter cage that surrounds the galaxy. Scientists can get a better idea of M33's hidden mass and try different ideas about the structure of the ring by simulating how they move. But it's not always easy to spot them. Tidal streams are incredibly faint, often less than 1% the brightness of the night sky. Finding them requires stacking exposures, filtering out background noise, and comparing data across multiple wavelengths. Instruments like the Subaru telescope and the Canada-France-Hawaii telescope have been instrumental in this cosmic detective work. Our Milky Way has gobbled up more than a dozen dwarf galaxies, including the Sagittarius dwarf, which is currently being torn apart and strewn across the sky. Andromeda too is surrounded by a web of tidal streams, some so massive they rival its own disk in size. M33's streams might be smaller, but they're no less significant. They are the signs of a galaxy that has grown through conflict. Some ideas even say that M33 may have been a part of a three-way exchange in the past. A smaller galaxy fell into it, and then it was pulled toward Andromeda. If that's true, then some of the stellar streams we see today could be stacked, with some coming from a small star that was eaten by another star, and some from Triangulum being stretched by its bigger brother or sister. Hidden stellar streams, faint clues of ancient mergers. Triangulum was thought to be the quiet one in the local group for a long time because it was a spiral galaxy that looked like it had never been in a fight. But just because it doesn't look like it was touched doesn't mean it was. New ultra-deep imaging is beginning to peel back that illusion, showing weak signs of violence that had been forgotten, ghostly stellar streams twisting around the edges of M33. It's possible that these streams, tense ribbons of stars that go far beyond the main disk, are the leftover material from galaxies that have been broken up over time. Unlike Andromeda, which boasts dramatic arcs and shell-like remnants from its galactic feasts, Triangulum's streams are shy. You won't see them in standard telescopes. They lurk at the very edge of visibility, requiring extremely sensitive cameras and long exposures to spot. But once detected, their structure tells a story. These aren't random stars. They're coherent tidal features, curved, elongated, and faintly rotating with the galaxy. Researchers used the Subaru telescope and the Canada-France-Hawaii telescope to look beyond the limits of Triangulum's main disk and found an extremely faint structure of stars that wraps around the galaxy in an open way. This is one of the most exciting discoveries to date. The stars in this structure are older and have less metal than the stars in M33's disk. This is typical of galaxies that are smaller and haven't developed as much. There is a neon sign flashing there. This is the remains of an old merger. Who did M33 eat then? We might never know for sure. Too few pieces are left, and the merger happened too long ago. Dwarf galaxies that circle a spiral like M33, on the other hand, may be stretched and torn over billions of years, leaving only a faint hint of their light. Triangulum doesn't seem to be as alone as was first thought, since it has streams like these. It may have been more active in the past than its smooth circular arms make it look like. These findings also force us to rethink how small spirals grow. Triangulum might not have undergone major collisions like Andromeda, but it likely still fed on a diet of dwarf galaxies, slowly, gently, over cosmic time. Each stream we detect today might represent one such snack, each adding just a little bit of mass to the halo, a few more stars to the outskirts, and another page to the galaxy's hidden history. More importantly, these faint streams help refine models of dark matter. When a dwarf galaxy is torn apart, its stars follow one path, but its dark matter halo follows another. By comparing the motions of stellar streams in M33 to simulations, researchers can infer how dark matter behaves during a disruption. This allows Triangulum, ironically, to serve as a testbed for dark matter studies, despite its relatively calm appearance. But finding these streams isn't easy. Their surface brightness is ridiculously low, often below 30 magnitudes per square arcsecond. That's hundreds of times fainter than the night sky itself. Only with advanced noise reduction and stacking techniques can these filaments be separated from the background. Some of them might not be visible at all from Earth. At least not yet. The James Webb Space Telescope and future missions like the Nancy Grace Roman Space Telescope could be game changers here, offering deeper views and sharper contrast. There's tentative evidence that one of Triangulum's stellar streams may have been triggered by a past flyby with Andromeda. Some models suggest that M33 didn't just brush past M31. It may have had a gravitational dance that pulled at its outer disk, stirred up its stars, and possibly disrupted one of its own dwarf companions. If that's true, then some of the debris we see might not even belong to M33, but to a smaller galaxy caught in the crossfire. This completely changes the plot of Triangulum's story. It not only took over other people, but it may have been caught up in someone else's story. And just like footprints in the snow, these secret trails left by the stars show us where it has been, even if its arms look nice and clean. Stellar halo ancient light at the edge of Triangulum. You can go past the bright spiral arms of Triangulum, the clusters, the clouds, and the thick fields of gas to reach an area that is neither empty nor bright, but very old. This is M33's stellar ring, a place where old stars float around alone in the dark. It's not exciting. In ultraviolet light, it doesn't glow, but it holds the most important secrets about the way the galaxy came to be. The stellar halo of a galaxy is a vast spherical region surrounding the visible disk. It contains some of the oldest stars known, low metallicity relics that formed in the early universe, before galaxies took on their modern shapes. In Triangulum's case, this halo is faint but undeniable. extending thousands of light-years in every direction beyond the main disk. Unlike the structured spiral arms or clustered star nurseries, the stars in the halo are scattered and diffuse. They don't rotate with the disk. Instead, they follow eccentric orbits, bobbing up and down, out of sync with the main galactic rhythm. This lack of order is a clue, because many of these stars weren't born in M33 at all. They were taken. An important part of Triangulum's halo is probably made up of pieces of dwarf galaxies that it has eaten up over billions of years. When smaller galaxies hit M33's gravity, they get ripped apart, and their stars, especially the oldest ones that don't have much metal, get splattered in long, looping paths that make up the ring. Each of these stars has a unique chemical signature. Astronomers can tell which ones are immigrants and which ones are native-born by looking at what they are made of. The stellar halo becomes a time capsule. It holds memories of every merger event, every close encounter, and every cannibalized companion. Think of it as a fossil record in starlight, whispering stories about a time before M33 became the graceful spiral we see today. Detecting this halo is no easy task. It's incredibly faint, blending into the blackness of space. But with deep field imaging from telescopes like Subaru and Pan-STARRS, astronomers have managed to isolate individual stars in this outer region. What they've found is stunning. Stars as old as 12 billion years, with chemical signatures suggesting they formed in environments far less enriched than Triangulum's inner disk. Some of these stars belong to faint streams, leftovers from swallowed dwarf galaxies. Others drift alone, slowly decaying in orbit, pulling M33's halo into an ever-changing mosaic. Unlike the Milky Way, which has a well-studied and extended halo filled with globular clusters and satellite galaxies, M33's halo is more subtle. It's a whisper compared to the roar, but that whisper is loaded with insight. There is even a theory that says Triangulum is still putting together its ring. The Milky Way and Andromeda have both been through several big mergers, but M33 may be in a more peaceful stage of growth. If it's true, the halo could be a glimpse into the early years of a spiral galaxy, like a picture from when the universe was a teenager. But the halo isn't just ancient, it's dynamic. Every interaction M33 experiences, whether it's with a passing dwarf galaxy or the gravitational pull from Andromeda, adds or subtracts from the halo's mass. Over cosmic timescales, it may grow or erode, depending on what's pulled in or pulled away. There is even a theory that says Triangulum is still putting together its ring. The Milky Way and Andromeda have both been through several big mergers, but M33 may be in a more peaceful stage of growth. If it's true, the halo could be a glimpse into the early years of a spiral galaxy, like a picture from when the universe was a teenager. Sometimes, stars in the halo can also get away from the disk by being thrown out by supernova kicks or collisions with other stars. These fast-moving visitors are uncommon but interesting because they show another way for stars to get to the edge of a galaxy and stay there. Dwarf satellites, Triangulum's tiny companions. Big galaxies rarely travel alone. Like moons to a planet, small dwarf galaxies often cling to the outskirts of giants, orbiting them for billions of years. The Triangulum Galaxy, or M33, may be modest in size compared to the Milky Way or Andromeda, but even this graceful spiral isn't without its entourage. These are the dwarf satellites, tiny faint galaxies that hover on the fringes of Triangulum's influence. They're not flashy. You won't see fireworks of star formation or bright spirals, but they play a crucial role in the cosmic story, both as relics of the early universe and as ongoing contributors to the evolution of their larger host. For a long time, astronomers weren't sure if M33 had any true satellites. Unlike Andromeda, which boasts a rich collection of dozens of companions, or the Milky Way, which is orbited by the Magellanic Clouds and Sagittarius Dwarf, Triangulum seemed to be a bit of a loner. Part of that impression came from the fact that M33 is smaller and less massive, meaning its gravitational reach isn't as extensive. Another part came from pure observational difficulty. These satellites are dim, diffuse, and often hide behind the background noise of the universe. But deep surveys have begun to change that. Telescopes like Pan-STARRS and the Sloan Digital Sky Survey, SDSS, have identified several ultra-faint candidates around M33, dwarf spheroidals and irregulars that may be loosely bound to the galaxy. These are some of the faintest galaxies ever detected, with luminosities barely brighter than a single globular cluster. Yet they may contain dark matter halos hundreds of times their visible mass. The star, Andromeda Dabtiu, is one of these possible partners. It was first found to be a satellite of Andromeda, but later research suggested that it might be closer to M33 in terms of gravitational pull. This would make it a very rare find, a possible shared satellite or even a satellite of a satellite. If that turns out to be true, it would be the first proof of a moon on a galaxy scale. These small satellites aren't just pieces of space junk. The chemicals that make them up help us understand how galaxies formed in the early universe. Many of them are metal poor because they are full of old stars that were never renewed by big explosions of stars. It looks like the tides are upsetting some of them because Triangulum's gravity is pulling them apart as they loop closer together in their circles. Their motion, tracking the orbits of these tiny galaxies, helps refine the mass estimate of Triangulum itself. Just how heavy is M33? That answer depends a lot on how fast and far these satellites are moving. If they orbit tightly, Triangulum might be heavier than it looks. If they drift loosely, maybe it's more lightweight. There's also the possibility that M33's lack of satellites is itself a clue. In the LCDM model of cosmology, galaxies like M33 should host dozens of dark matter-dominated mini-halos, many of which should contain visible dwarf galaxies. If we're only seeing a few, where are the rest? This missing satellites problem is a hot topic in astrophysics and forces scientists to re-evaluate either the sensitivity of our surveys or the models of galaxy formation themselves. More satellites could be found in the future. When the Vera C. Rubin Observatory, formerly LSST, starts up, it will map the night sky with a level of clarity and frequency that has never been seen before. This could show galaxies circling M33 that we can't see right now, fellow travelers waiting for their turn in the story. Transient X-ray bursts, moments of galactic violence. Triangulum may appear to be a calm, spiraling mass of stars, but there are quick, violent bursts going on behind that calm exterior. Moments that come and go like the blink of an eye in space. We're talking about transient X-ray bursts, which are short, bright explosions from binary systems, black holes, or neutron stars that fill the sky with incomprehensible fire for a short time. These events don't last long. Some flare for seconds, others for minutes or days, but they always leave a signature in the X-ray sky. Triangulum, observed through the sharp eyes of telescopes like Chandra and XMM Newton, reveals multiple transient X-ray sources, some repeating, others one-off flashes that vanish as quickly as they came. What causes them? Most of the time, these bursts originate from compact stellar remnants, neutron stars or black holes, locked in binary systems with a normal star. The smaller dead object siphons gas from its companion in a gravitational tug-of-war. As the gas spirals inward, it heats up, forming an accretion disk. This disk becomes an inferno, emitting X-rays as matter races toward oblivion. Occasionally, the system becomes unstable. A sudden pile-up or collapse in the disk triggers a violent flare, a transient X-ray burst. People can't see these X-ray events at all, even though they are some of the brightest in the world. They wouldn't have been seen without special binoculars, but by looking at the sky with X-ray telescopes, we've found dozens of these kinds of explosions inside M33. Some of them happen in tight binary systems that are not even a few million years old. Others come from dead stars that have been eating for a very long time. A particularly interesting class of these events are Type 1 X-ray bursts, thermonuclear explosions on the surface of a neutron star. When enough hydrogen or helium accumulates on the star's surface, it detonates in a runaway reaction. The result is a brief, intense flash of X-rays, followed by a return to normal. These bursts are not just dramatic, they're predictable in certain systems, allowing astronomers to study them in real time. Then there are pairs of black holes. These monsters don't explode on the surface, but when they flare, they do so very strongly. For a short time, their X-ray blasts can be as strong as whole galaxies. In Triangulum, a few possible black holes have been found by the rapid brightening of their X-rays, which is usually followed by times of inactivity. This kind of system goes off every few years or decades and then stops. It's called an X-ray nova. What makes these bursts so valuable to astronomers is their timing and energy profile. Every X-ray pulse, every decay curve is a clue. It tells us about the mass of the compact object, the spin, the magnetic field, even the composition of the material it's consuming. In many ways, a single flare can reveal more about the invisible parts of a galaxy than years of optical observation. Sometimes, transient X-rays come from flaring stars, active galactic nuclei, or even supernova shock waves reverberating through the interstellar medium. These are rarer in M33, but not impossible. In fact, given how young and star-forming Triangulum is, it's likely a hotbed for high-energy surprises that we haven't fully mapped yet. There are also ripple effects from these bursts. The strong radiation can heat up gas clouds nearby, stop stars from forming, or even ionize parts of the space between the stars. A very strong burst could even wipe out the atmosphere of a planet that gets in its way, but no such worlds have been found in M33 yet. Transient X-ray bursts are fast, bright, and hard to plan for. They're like cosmic camera flashes, but each one records an important event. A black hole taking in food, a neutron star going off, a disk of gas falling apart. Even though these things happen all the time in the universe, they are often missed, especially in close galaxies like Triangulum. Ultraviolet glow, where radiation meets resistance. Triangulum may look beautiful in visible light, but it's in ultraviolet, UV light, that this galaxy really shows how young and active it is. UV eyes let you see more than just stars when you look into M33. You can see points of pressure, pushing back. Radiation and matter are in a high-energy tug-of-war that is quietly shaping the future of whole star systems. Ultraviolet light, particularly from young, hot, massive stars, is relentless. It blasts out of star-forming regions like NGC 604, flooding the surrounding gas with ionizing radiation. These UV photons are powerful enough to strip electrons from atoms, carving out bubbles and illuminating hydrogen-rich zones known as H2 regions. But that's only half the story. The other half is resistance. Interstellar dust and dense molecular clouds absorb UV light, sometimes reflecting it, sometimes extinguishing it altogether. In the process, this dust becomes energized, heating up and re-radiating at infrared wavelengths. So while ultraviolet emissions point us to where stars are born, the shadows they cast tell us where they struggle to emerge. How patchy and uneven Triangulum's UV profile looks is one of the most interesting things about it. The star-forming disks in galaxies with smoother UV glow are not like the UV glow in M33. It is broken up into clumps and arcs. This points to a kind of cosmic feedback loop. When a new star forms, it fills its surroundings with radiation. This stops more formation in nearby areas by blowing out gas and ionizing the stars nearby. Ultraviolet radiation is both the fuel and the firebreak. It triggers collapse in some places, but shuts it down in others. This trigger and suppress model is crucial to understanding how galaxies like M33 grow over time, especially since Triangulum is considered a lower mass spiral galaxy without a central bulge to dominate dynamics. UV observations reveal how this growth occurs from the inside out, led by scattered starbursts, rather than a sweeping galactic engine. Scientists have used tools like NASA's GALEX satellite, Galaxy Evolution Explorer, to make very detailed ultraviolet maps of M33. These pictures show groups of hot stars that are only a few million years old and are surrounded by clusters and filaments. These zones often combine with H2 regions that can be seen or infrared-emitting dust clouds, making a more complex picture of how stars are born and die. But there's another hidden role ultraviolet light plays: chemical evolution. When UV light hits carbon-rich molecules or ices in dust grains, it triggers photodissociation and complex reactions. This is how basic elements are transformed into more complex organic molecules over time. These reactions don't just influence chemistry, they may play a part in the formation of planetary systems. In M33, it's easy to see where UV light is strongest. The arms on the outside are clearer, less dusty, and have a better UV contrast. In the middle, where the dust lanes get thicker, UV light is spread out and absorbed more. So, there's a radial gradient, and you can tell how important young stars are by how well their light escapes. Still, that light isn't going completely ignored. The way UV rays and cosmic dust interact has also become one of the best ways to study how fast stars are forming in Triangulum. When mixed with far infrared data, it helps scientists figure out not only where stars are being born, but also how quickly they are being born. M33 has a small total mass, but it forms stars surprisingly quickly, and its UV glow shows that it's still very much a player in the cosmic game. We learn how light and matter interact in disk galaxies like the Milky Way in its early stages by looking at M33's ultraviolet profile. The ultraviolet picture of Triangulum shows how gas and dust block light, how young stars shine, how light is absorbed and scattered, and all of these changes over time. They can be heard in galaxies all over the place. Supergiant life cycles, born bright, die loud. When you're in the Triangulum Galaxy, beauty often only lasts for a short time. Some of the biggest stars in the universe are burning at full speed in the spiral arms and bright nebulae. These are called supergiants. These stars aren't like other ones. They are giants with dozens of times the Sun's mass. They live quickly and die young in the most dramatic ways you can think of. A supergiant begins its life in one of M33's bustling star-forming regions like NGC 604. In the cold, dense cores of molecular clouds, gravity pulls together vast amounts of gas until nuclear fusion ignites. When the core mass is large enough, it doesn't form a sun-like star, it forms a monster. These stars can be over 100,000 times brighter than the Sun and up to 1,000 times its diameter. Blue supergiants in particular dominate the younger regions of M33. Their surface temperatures can exceed 30,000 degrees Celsius, flooding the galaxy with ultraviolet radiation that shapes nearby gas clouds. But their brightness comes at a cost. These stars burn through their hydrogen fuel in just a few million years. For comparison, the Sun has a lifespan of about 10 billion years. As the hydrogen runs out, fusion shifts to heavier elements: helium, carbon, oxygen, and beyond, each new stage burning hotter and lasting shorter. The core becomes an onion of nuclear reactions, with layers stacked like a countdown to collapse. Red supergiants emerge during this stage too, cooler on the surface but still enormous and unstable. There are a lot of both red and blue supergiants in Triangulum. Hundreds of them have been named thanks to observations made with tools like the Hubble Space Telescope and observatories on the ground. These observations show different steps in the life cycle of supergiants. Some are about to blow up, while others have only just started to burn. Some are in the strange yellow supergiant phase, where they are teetering between blue and red as they lose mass and fight gravity. The death of a supergiant is perhaps the most violent event in Triangulum's storybook. When fusion finally produces iron in the core, the process halts. Iron can't produce energy through fusion, it only absorbs it. The core collapses under its own weight in a fraction of a second, triggering a supernova explosion. The outer layers are blown apart, enriching the galaxy with heavy elements like gold, uranium, and lead. Which things are left behind rely on how heavy the star was. Some of them leave behind neutron stars, which are very dense leftovers that spin and pulse in the dark. Others fall apart into black holes and disappear completely, leaving only their gravitational pull behind. In either case, the explosion leaves behind a supernova residue, which is a ring of gas that glows and expands and can be seen in X-rays, radio waves, and sometimes even visible light. M33 has several known supernova remnants traced back to supergiant deaths. Each one is a cosmic scar, a relic of a star that lived fast and died with a bang. These remnants don't just fade away. They interact with the surrounding gas, triggering new waves of star formation or carving massive voids known as supershells. The galaxy is shaped by supergiants even after they die. Their heavy parts help make new planets and stars. Their shockwaves move energy around the disk in a new way. Their light, which travels through space, tells the story of their short but important lives. There is beauty in the way these stars live. They are famous people in the universe. They are smart and powerful, but their lives are doomed to end tragically. These stars want to be known, while the sun will quietly fade into a white dwarf. The galaxy is changed by the blasts that shake the spiral arms and change the chemistry of the space between them. The missing bar. Does Triangulum have a galactic spine? As the backbones of galaxies, bars are straight, bright structures made up of stars and gas that cut through the middles of many spiral galaxies. They pull gas inward, start bursts of star formation, and can even change the path of a galaxy. The big question is why Triangulum, the third largest galaxy in our local group, doesn't have one. Does it? Astronomers thought for a long time that M33 was a standard unbarred spiral galaxy, which means it didn't have any bars in the middle. High-resolution pictures taken with visible light show that Triangulum's arms curve outward easily from a bright center, and there is no clear bar to be seen. That made people think of it as simple, symmetrical, and barless, which made it stand out from its bigger cousin Andromeda and even our own Milky Way, which both have big bars. But things started to go wrong when scientists dug deeper. Images taken in the infrared, especially by the Spitzer Space Telescope, started to show signs of a different story. Infrared light, which makes it easier to see dust and cooler stars, showed a slight shift in the middle of M33. It wasn't a big, obvious bar, but it looked just off-center and thick enough to make people look twice. Triangulum might be hiding a bar that is too faint to see with the naked eye. It's called a pseudobulge or weak bar by experts if it does. There isn't a straight line of stars here like there is in the Milky Way. What you see is more of a soft distortion, like the galaxy has a bendy backbone that only shows up in certain lights. Some computer models show that even weak bars can cause spiral density waves and change the way stars form across a disk. That means that M33's bar, if it exists, might be quietly controlling how its spiral arms change over time. To confirm this, astronomers turned to gas kinematics, the motion of hydrogen gas inside the galaxy. In galaxies with bars, the gas tends to show certain streaming motions, curved paths, velocity twists, or resonance patterns near the center. M33's gas doesn't scream bar, but it does whisper strange curves in places where a weak bar might stir up turbulence. Why is M33 so shy if it has a bar? It's possible that Triangulum doesn't have enough center mass to hold a more visible one in place. Most bars are held up by a thick bulge of stars in the middle, but M33 doesn't have much of a bulge. This means that the center of it has less gravity pull to hold a thick bar in place. In its place, we could see a bar that never fully formed, or one that did form but is already breaking apart. This has to do with a bigger question about how Triangulum has changed over time. Bar formation is influenced by interactions between galaxies as well as the science inside the star. The bar in the Milky Way may have gotten bigger when it collided with or flew close to other galaxies in the past. Triangulum, on the other hand, seems to have had a calmer life, at least until it started flirting with Andromeda through gravity. M33 may be in a more pure and unhindered state because it hasn't had a troubled past. But pristine doesn't mean boring. If Triangulum is managing spiral structure without the architectural help of a strong bar, that's a scientific goldmine. It means we're witnessing a different route to galactic organization, a case where spiral arms and gas flows are driven by disk instabilities alone. To test this further, Astronomers are combining data across wavelengths: optical, infrared, ultraviolet, and even radio. Some studies suggest that central star clusters in M33 rotate faster than their surroundings, a hint that there might be a rotating inner component, a minibar or dense clump that behaves like one. Others model the gravitational potential of M33's core and find signs of asymmetry. Another point in favor of a subtle bar. Planetary nebulae, the glittering death of sun-like stars. Not every star dies in a big blast in the big cosmic show. Some leave in a quiet way, but in style. In the Triangulum Galaxy, these soft goodbyes come in the form of planetary nebulae, which are gas rings that glow and grow through space. Stars like our Sun leave these behind. No matter what the name says, they are not worlds. Astronomers in the past thought they were planetary disks because they were round, so the name stuck. But what they really show is the last bright breath of a star that is dying. These nebulae are scattered all across M33, glowing in vibrant hues of green, red, and blue. They are often found in the galaxy's older stellar populations, regions where intermediate mass stars have lived out their multi-billion-year lifespans. When these stars exhaust their nuclear fuel, they don't collapse into black holes. Instead, they swell into red giants, puff off their outer layers, and expose their hot cores to space. The end product is beautiful. The exposed center, which is now a white dwarf, sends out strong ultraviolet light that ionizes the gas being thrown out, making it glow like a lantern in space. These glowing shells can be light years across and form beautiful halos that last for tens of thousands of years before fading into the background of the galaxy. As you look through Triangulum, planetary nebulae mark the end of star episodes. Their importance comes from what they show about the structure of the galaxy. When stars die in this way, they leave behind elements like oxygen, nitrogen, and carbon that make the space around them better. Even though these aren't the heavy metals that supernovae make, life as we know it still needs them. Astronomers can learn about how elements were formed in the galaxy's past by looking at the chemical signatures of planetary nebulae in M33. What's fascinating is how different planetary nebulae look depending on their surroundings. In denser regions of M33, like the inner disk, these nebulae often appear more compact and symmetric. Farther out in the galactic halo or outer arms, they tend to be larger, fainter, and sometimes asymmetrical, likely shaped by lower gas densities and weaker stellar winds. Triangulum also helps scientists understand how planetary nebulae evolve over time. By comparing nebulae at different stages, some freshly formed, others near the end of their glow, we can watch the gradual expansion and dimming of these structures. Instruments tuned to specific emission lines, like those from doubly ionized oxygen, allow astronomers to track gas temperature, density, and velocity across the nebula. The total number of planetary nebulae identified in M33 is in the hundreds, with many more suspected to exist just beyond current detection limits. Surveys using narrowband filters and large telescopes continue to find new ones every year. Each new discovery helps fill in the puzzle of how stars like our Sun live, die, and recycle their material back into the galaxy. The fact that these items could be used to measure the universe makes them even more interesting. Because some planetary nebulae stay pretty bright at their brightest, they can be used as standard lights to figure out how far away something is. In Triangulum, they add another step to the cosmic distance ladder and help us get a better idea of how far away this galaxy really is. The stellar nebulae have a feeling to them as well. These deaths are beautiful, not like explosions or black holes which are full of chaos and death. A star that used to fuse atoms together for billions of years doesn't blow up. It glows, lessens, it gives back. It turns into a work of art made in ultraviolet and infrared light in its last act. In M33, these old stars give the story of the galaxy more depth. They show that ends don't have to be violent all the time. It's possible for a star to leave us with grace, leaving behind color and heritage instead of quiet and noise. Low surface brightness skirts, M33's faint forgotten edges. Galaxies not all bright like a city at night. Some places are more like back roads. They are dim, quiet, and simple to miss. That's where the Triangulum Galaxy's low surface brightness bands come in. These very faraway areas are so dim that they almost blend into the background of the universe, but they hold important information about how the galaxy grew, how it collided in the past, and how it is moving now. If you were to look at M33 through a standard optical telescope, you might think the galaxy ends where its well-defined spiral arms fade out. But peer deeper, using long exposure times and instruments sensitive to faint light, and something ghostly begins to emerge. Stretching tens of thousands of light years beyond the visible disk is a halo of diffuse stars and gas. This is the low surface brightness skirt, an extended, faint envelope of matter that exists far beyond what the eye usually catches. Hugely important, these clothes show us what the galaxy has eaten. Smaller satellite galaxies and loose groups of stars are pulled in by galaxies like M33 as they grow. Gravitational forces tear these things apart when they get too close, sending stars to different parts of the galaxy. These torn pieces don't always make the news, but they settle on the edges and become part of this weak structure around the edges. It's cosmic history with layers of stars. Recent surveys using deep imaging techniques, like those from Subaru and Pan-STARRS telescopes, have confirmed that M33's outskirts contain stellar substructures, patchy, asymmetrical features that break the neat disk symmetry. Some of these may be leftover tails from minor mergers. Others could be ancient streams of stars pulled out by past encounters with Andromeda, which lies just 750,000 light-years away and is slowly pulling M33 toward it. These skirts also stretch our understanding of how galaxies evolve. In the inner disk of M33, star formation is active and high-density gas fuels new stellar births. But in the low-brightness outskirts, things slow down dramatically. Gas densities drop, metallicity plunges, and star formation, practically dormant. Yet even here, faint clusters of stars still cling to existence, suggesting that these zones were once more active, or that slow, quiet processes still build stars in extreme conditions. From a structural standpoint, M33's outskirts challenge assumptions about where a galaxy ends. In older models, a galaxy was its bright disk and nothing more. Now we know better. These outer skirts can account for a significant portion of a galaxy's mass. In fact, they're vital for measuring dark matter distributions. Because they orbit farther from the core, their motion helps map out the gravitational pull beyond the reach of visible light. If their speeds stay high despite little mass being visible, it's more evidence that dark matter exists in a halo around the galaxy. This is also where we study the health of the galaxies. Do the outer stars still spin at the same speed as the center disk? Or do they seem to be moving, wobbling, or ripple? These small clues show how safe the galaxy's structure really is, and if it might be moving toward merging with another local group member. Even the dust out here behaves differently. In most of M33, dust lanes track the spiral arms and trigger star formation. But on the outskirts, dust is sparse, clumpy, and cold. Infrared scans from telescopes like Herschel have picked up whispers of cold dust emissions, a hint that even in darkness, there's something stirring. The fact that the low surface brightness skirt is so hard to see is one of its most artistic qualities. You need to be patient in these areas. The photons need to come first. Allow the long shots to add up. Get rid of the noise. Take away the stars. The shape doesn't become clear until then. A ghost of Triangulum, bigger than anyone thought, quietly stretching across the space. It's like discovering that someone you've known your whole life has a hidden history tattooed across their skin, faded but real. That's what M33's faint outer edge is, a hidden history, a record of violence and survival, expansion and silence. H1, supershells cavities carved by supernova chains. There are different kinds of chaos in the twisting arms of the Triangulum Galaxy. Sometimes it looks like fire and rage. It looks like a hole sometimes. Not a black hole or a void, but a huge bubble hundreds of light years wide in the space between the stars. These are H1 supershells, which are huge holes in the gas in the galaxy that were made by the force of many supernova blasts over millions of years. The H1 part means we're dealing with neutral hydrogen atoms that haven't lost their electrons. It's the most common form of gas in the universe and a key ingredient in galaxy evolution. The supershell part refers to what happens when a bunch of massive stars live, burn, and die in close quarters. Each one ends its life in a supernova, and each explosion sends out shockwaves. When these shockwaves overlap and reinforce each other, they sweep up the surrounding gas into a gigantic expanding bubble. In M33, astronomers have identified dozens of these supershells. Some are relatively small, just a few hundred light years across. Others are absolutely monstrous, stretching over 1,000 light years wide. These aren't subtle features either. When mapped in 21 cm radio waves, which trace neutral hydrogen, these shells show up as distinct voids surrounded by dense gas walls, like cavities in a sponge. So what makes them happen? There are a lot of stars in the nursery, where dozens or even hundreds of big stars are born. These stars don't stay alive long and die young. They start going supernova one by one in a few million years. With each blast, the shock front grows, pushing more gas outward and hollowing out the area. This makes a wall of force in space that can last for tens of millions of years. The structure of these supershells tells us a lot. Their size can reveal how many supernovae were involved. Their shape can hint at what kind of environment they blew through. Denser areas resist expansion, while thinner regions allow the bubble to grow lopsided. Their motion, tracked through Doppler shifts in the hydrogen emission lines, gives clues about energy, speed, and even age. But supershells don't just mark death, they also make new things. As these rings move through the galaxy, their walls push gas forward, making it denser. When this happens, it can start new waves of star formation. H1 supershells work like space dominoes in this way. The death of one generation of stars makes room for the birth of the next generation through sheer explosive power. The galaxy itself is built with this beautiful feedback loop in mind. Some of the most impressive supershells in Triangulum are located in the outer spiral arms. Here, the interstellar medium is less crowded, which allows the shells to grow bigger before they collapse or lose energy. In the inner disk, they're often smaller but denser, interacting with more gas and potentially sparking more concentrated bursts of star formation. There are even supershells that look like they have broken, shooting out into the galaxy's halo. It's possible that these chimneys let hot gas exit, letting energy and matter leak out into the space around the star. This process might be very important for controlling M33's internal pressure and even changing how metals are spread out from the center to the edges. It's crazy that some of these H1 supershells are so big that they touch each other. That makes the galaxy's gas disk look like Swiss cheese, with holes, bubbles, and shells that fit together. It's not just pretty to look at. This complicated structure also changes how sound waves move, how magnetic fields are formed, and how energy goes from one place to another. Hypervelocity stars, shooting out of M33 at escape speed. Consider a star that moves so quickly and without any limits that it breaks free from the pull of a whole galaxy and goes into the dark, unknown area between galaxies. These are hypervelocity stars, which are like cosmic cannonballs, thrown at speeds so crazy that not even the force of the galaxy can stop them. Triangulum also has them, though. Most stars are slowpokes. They orbit the center of their galaxy like clockwork, steady, stable, and gravitationally obedient. But then there are the rule breakers. Hypervelocity stars are rare stellar outlaws that move so quickly they exceed the escape velocity of their home galaxy. For M33, that's about 300 kilometers per second at its outer edge. These stars don't just wander, they flee. How does that happen? Some ideas are very important, and they all have big parts. What is the most common reason? A death dance close to a giant black hole. Two stars orbiting each other make up a binary star system. If it gets too close to the black hole at the center of the galaxy, its gravity can break the pair apart. One star takes a bite. The other person yelled into space very quickly. Triangulum's core doesn't have a confirmed supermassive black hole, at least not one as massive or chaotic as the Milky Way's Sagittarius A asterisk. So if M33 is launching hypervelocity stars, something else might be doing the kicking. Maybe one more thing? Stellar slingshots from reactions between three stars. If three stars get into a fight over gravity, one can be thrown out quickly while the other two stick together stronger. Or think about stars that have broken away from large groups. When one goes supernova, the partner star can be thrown out into space without any support and by itself. Stars with very fast speeds are hard to find in Triangulum, but it's not impossible. Outliers are stars that are going too fast in the wrong direction. They can find options that don't fit in with the rest of the galaxies by measuring their radial velocity, which is how fast they're moving toward or away from us. People pay attention when a star is young, hot, flying by itself, and moving at an extremely fast speed. Some of these stars are moving at over 1,000 kilometers per second, fast enough to leave the galaxy and never look back. These aren't gentle drifts into the void. They're high-speed escapes, propelled by immense forces that we're only just beginning to understand. Hypervelocity stars don't just fascinate because of their speed. They're also messengers. By tracing their paths backward, scientists can figure out where they came from and what might have thrown them. It's like forensic astronomy. A single fleeing star could reveal a hidden black hole, an ancient supernova, or a cluster torn apart by violent feedback. Where do these stars go if they get away from M33? You go straight into the cosmic medium, which is a cold, dark desert with few stars and little gravity. These stars end up being cosmic orphans, shining light on spaces between galaxies that would otherwise be dark. They cool down, fade, and move on in silence over time. But their existence changes how we think about galaxies. If M33 can launch stars out into the universe, it means energy is being transferred, mass is being lost, and boundaries are more porous than we thought. Hypervelocity stars are like escapees from a prison no one knew had doors. They're also useful in a strange way as probes into the universe. Since they go such long lengths, they can be used to study things like the shape of a galaxy's gravity field, where dark matter is found, and even how the local group is put together. Some are thought to be traveling through space on paths that will finally bring them close to the Milky Way. Metallicity gradients. Chemistry tells a story. Most likely, when you think of stars, you picture how bright or what color they are. But there is another, much less obvious but just as important trait that shows where they came from, how long they live, and even the past of their galaxy. They are metallic. And in the Triangulum Galaxy, differences in metallicity make a chemical picture that tells a story that has been formed over billions of years. Metallicity, in astronomy, doesn't mean actual metal like iron bars or coins. It refers to the amount of elements heavier than hydrogen and helium inside a star. Think carbon, oxygen, iron, all the stuff forged in stellar furnaces. The higher the metallicity, the more generations of stars had to exist before that star formed. In other words, metallicity is a record of stellar ancestry. Now, here's where it gets interesting. When astronomers study galaxies like M33, they don't just look at overall metallicity. They study how it changes across distance. This is the metallicity gradient, a smooth, or sometimes not so smooth decline in metal content as you move from the galaxy's center to its outer edges. That curve is very clear in Triangulum. The heavy elements in the center regions were formed by many generations of stars dying and coming back to life quickly. These are places where a lot of stars are being formed, and supernovae have been adding new metals to the space between the stars for billions of years. As you move outward, though, the metallicity drops. Stars on the outskirts tend to be older, less evolved, and born from gas that hasn't been as heavily processed. These regions are quieter, less turbulent, and more pristine in their chemical makeup. Astronomers detect these metallicity differences by studying the light from stars, star clusters, and gas clouds. Spectroscopy reveals the fingerprints of elements like oxygen, nitrogen, and sulfur. Emission lines from H2 regions and absorption features in stellar atmospheres allow researchers to quantify just how metal-rich, or metal-poor, each region of M33 really is. So, what does this slope tell us? First, it helps us figure out how the galaxy came to be. A high gradient means that stars are forming quickly in the middle at first, but then more slowly on the edges. A lower gradient could mean that galaxies have merged or that gases are mixing on a big scale. The curve of Triangulum is pretty smooth, which means it hasn't been disrupted much in its life, at least compared to Andromeda. Second, it tells us about the movement of gas. Over time, inflows of pristine gas from the cosmic web can dilute the central metallicity. Outflows, driven by supernova winds, can carry enriched material from the center to the halo. These dynamics can subtly reshape the chemical profile of the galaxy. In M33, there's also evidence that the metallicity gradient isn't perfectly uniform. Some regions show pockets of enrichment, likely remnants of supernova clusters or compact bursts of star formation. Others appear more depleted, as if gas has been siphoned away or hasn't been enriched by enough stellar death. Metallicity has an effect on the stars as well. Stars with less metal burn hotter and have different lives than stars with more metal. They can make different kinds of planets because of this. It also changes the mass of the black holes they leave behind and even how bright they look in telescopes. So knowing what chemicals make up M33 isn't just about its past, it's also about what will happen in the future. And then there's the link to the local group. By comparing the metallicity gradient of Triangulum with those of the Milky Way and Andromeda, astronomers get a window into how different galactic environments shape chemical evolution. Triangulum's gradient is more like the Milky Way's, smooth, predictable, and relatively unbroken, while Andromeda's is more chaotic, scarred by past collisions. That each star in M33 holds a part of the story of the galaxy, written in atoms instead of words, is crazy. Every part of it, from the air it breathes out to the iron at its core, was made by stars that came before it and was passed down like a cosmic property. CO emissions, the map of dense molecular gas. In the huge process of star creation, thick molecular gas is the most important part. Cold, thick clouds of hydrogen are where stars are made. This is where gravity takes over and starts fusion. In a strange way, hydrogen is almost impossible to see. How are we going to find it? Carbon monoxide is an unusual cosmic explorer that helps researchers make maps of the hidden structures of galaxies like Triangulum. Carbon monoxide, or CO, is the tracer gas of choice. It's not nearly as abundant as hydrogen, but it's easier to detect. When CO molecules spin, they emit radio waves that can be picked up by powerful telescopes like ALMA or the IRAM 30-meter dish. These emissions reveal where dense, cold gas is hiding, particularly in the galaxy's inner spiral arms, where stars are forming in bulk. In M33, Colorado emissions tell a revealing story. Surveys have shown that Triangulum's molecular gas is heavily concentrated in a band stretching across its inner disk, roughly within 5 kiloparsecs of the galactic center. This is where the spiral arms are most tightly wound, and where the gravitational forces compress clouds into fertile star-forming zones. It's interesting that the CO spread isn't smooth. It's clumpy and broken up into huge molecular clouds that are tens or hundreds of light years wide. These clouds are where many generations of stars can form. These clouds are also not still. They spin, bump into each other, fall apart, and get blown apart by the stars they make. CO lets scientists see how this cycle moves. The contrast between CO and H1 maps is also dramatic. While H1, neutral atomic hydrogen, extends far out into the galaxy's disk, forming a diffuse halo, CO is a much more local affair. It hugs the galactic plane, marking only the densest, coldest regions where hydrogen molecules can form and persist. In a sense, Colorado draws the skeleton of M33's inner life, its beating, breathing, stellar-making heart. By analyzing the velocity of CO emission lines, astronomers can also learn about how gas is moving. Are molecular clouds orbiting smoothly? Are they being stirred by spiral density waves or disrupted by feedback from supernova? In M33, velocity maps reveal a surprisingly ordered rotation pattern, but with localized turbulence, especially near active star-forming regions like NGC 604. And CO isn't just a snapshot of where stars are forming now, it's a blueprint for where they're about to form. The presence of a giant molecular cloud means that, sometime in the next few million years, it's likely to collapse into new stars. By comparing CO maps with infrared surveys, which show warm dust heated by young stars, scientists can chart the galaxy's past, present, and future all at once. Also, there's the matter of metallicity again. The farther out in Triangulum you go, the harder it is to find CO because it forms more easily in places with lots of metals. This could leave a blank spot. There may be some molecular gas out in the spiral arms, but it can't be found because there aren't enough metals to turn it into CO. To fill in these holes, researchers are now looking into other traces, such as infrared dust emissions or deuterated hydrogen. CO emissions have also helped refine our understanding of Triangulum's structure. They've highlighted spiral arms that don't always show up in visible light, revealed offset shock fronts where gas piles up, and suggested that M33's star formation might be more self-regulated than previously thought, not just driven by spiral density waves, but also by feedback from the stars themselves. That's it for now. Carbon monoxide is like the highlighter pen that astronomers use. It shows where the densest material for making stars lives, how it moves, and how it responds to the forces in the galaxy. Triangulum would be a lot harder to figure out without CO. Intergalactic medium, the invisible bridge, between M33 and M31. There is a place between the bright swirls of Triangulum and Andromeda that looks like it has nothing in it, just another stretch of cosmic black. However, scientists now think that this nothingness could be something. A bridge. It's made up of a thin thread of gas and plasma that tugs at the two galaxies over 2.4 million light-years. Welcome to the cosmic medium, which is the universe's spirit web. For decades, astronomers suspected that galaxies weren't entirely isolated. Theories and simulations pointed to vast, low-density filaments, part of the cosmic web, that stretch between major galactic structures. But it's only recently that direct evidence began to emerge in the local group itself. Between M31 and M33, deep radio observations have revealed a faint hydrogen signal, hinting at a literal gas bridge spanning the void. It's not thick enough on this bridge to make stars. A telescope wouldn't help you see it. But you can tell it's there because of faint signals in the 21 cm hydrogen line, which is a radio frequency that shows cold neutral gas. The connection is very weak, but it keeps going. It looks like Andromeda and Triangulum aren't just neighbors. They're trading matter across a thread that goes back to before they were aligned the way they are now. The origin of this bridge is still debated. One theory suggests it's primordial, part of the larger cosmic structure that seeded both galaxies. In this view, M31 and M33 formed near each other because the gas was already denser in that filament, funneling material in both directions. Another theory says the bridge may be gravitationally induced, a leftover from a past close encounter that siphoned gas out of Triangulum's outer disk and slung it toward Andromeda like a cosmic thread. What if this bridge is fuel, a pipeline of cold gas that M33 or M31 could tap into, maintaining star formation over billions of years? If true, this could help explain how Triangulum, a relatively low-mass galaxy, sustains such a high specific star formation rate. It may not be doing it alone. It might be feeding off a subtle cosmic vein. The science gets even more interesting now, though. The gas in this bridge isn't just inactive. Observations show that ultraviolet radiation from both galaxies may have ionized some parts of it. That means this structure isn't a static relic. It's alive, moving, and being changed all the time by galaxy motion, star winds, and supernovae, a feedback loop on a huge scale. Some researchers also point out that this intergalactic medium could be the missing piece in simulations of M33's warped outer disk. The gravitational pull of this bridge, light though it may be, could subtly torque the spiral structure of Triangulum, especially in its outermost arms. If so, then the bridge isn't just a passive feature, it's actively sculpting the galaxy. What this bridge could mean for the future of the galaxy is even more interesting. M33 could be caught in the crash when Andromeda finally hits the Milky Way in 4 billion years. If the bridge is still there, it might pull Triangulum into the fight like a gravity tow line, or it might fight the pull and stretch like cosmic taffy before breaking. What happens to the local group in the end might depend on this unseen link. New missions like the Square Kilometre Array, SKA, may provide sharper images of this structure, mapping the intergalactic medium in unprecedented detail. If we can fully chart this bridge, we'll gain a clearer view not only of M33 and M31, but of how galaxies interact across space without ever touching. It's not just about collisions anymore, it's about connection. Milky Way versus Andromeda versus Triangulum, a galactic face-off. Let's have a fight to end this trip. Lots of galaxies, a group in the area, and 3 people with very different attitudes. Even though the Milky Way, Andromeda, and Triangulum are all close by, their stories, structures, and actions in the universe couldn't be more different. What do they do when they go up against each other? Start with the size. The big ones are the Milky Way and Andromeda. Both are about 220,000 light-years across and are home to between 100 and 400 billion stars. Triangulum, on the other hand, is the little brother or sister. It is only 60,000 light-years wide and has about 40 billion stars. But don't be fooled by its size. What M33 loses in mass, it makes up for in how clear it is. Andromeda, M31, is messy. It's the cosmic brawler, scarred by past galactic mergers, loaded with streams of cannibalized stars and hosting a massive central bulge that warps its inner structure. The Milky Way is a little more reserved, but still full of complexity. Warped outer disks, a central bar, and evidence of past galactic collisions, like the Sagittarius dwarf being shredded in real time. Triangulum? It's the cleanest of the 3. Its spiral structure is remarkably symmetric. It has no massive bulge, no major tidal scars, and fewer signs of past trauma. For astronomers, this makes M33 a kind of control group, an example of what a quietly evolving spiral galaxy looks like when left mostly to itself. Triangulum punches above its weight. Despite being a third the size of the Milky Way, it produces stars at a faster rate per unit mass. Its specific star formation rate is one of the highest in the local group, thanks to rich molecular clouds and efficient gas processing. Andromeda, by contrast, is winding down, a redder, older galaxy shifting toward quiescence. The Milky Way sits somewhere in between, still active, but not frantic. Even bigger differences can be found at the core. At the heart of both the Milky Way and Andromeda are supermassive black holes that are millions of times the mass of the Sun. The Triangulum doesn't. At the very least, if it does, the black hole is very small, no more than 3,000 solar masses. Some people say it doesn't even exist. That tells us a lot about how central black holes grow. M33 may not have had enough mass or activity to start a black hole. And what about their halos, the wispy ancient envelopes of stars and gas that surround them? Andromeda's stellar halo is massive and chaotic, evidence of many past mergers. The Milky Way's halo is complex too, filled with streams from devoured satellites. Triangulum's is much fainter and less metal-rich. It suggests a quieter past, with fewer collisions and a more stable evolution. Andromeda is barreling toward the Milky Way at about 110 kilometers per second. In around 4 billion years, the two giants will collide in a galactic mega-merger, transforming into a massive elliptical galaxy, sometimes called Milkomeda. Triangulum is nearby, but not on a direct collision course, yet. Simulations show it may get caught up in the chaos, possibly orbiting the merger remnant or even being swallowed into the fold. Some models suggest Triangulum may have had a past encounter with Andromeda already. A close pass a few billion years ago could have tugged on its disk, triggered star formation, and left subtle signatures in its spiral arms. It may not be a loner after all, but a distant echo in a cosmic family drama. Who is going to win the fight? When it comes to speed and mass, Andromeda is the best. The Milky Way is the perfect place to find both action and order. If you want to see what a spiral galaxy might look like without all the chaos, how about this? Triangulum came out on top. Triangulum has shown us a quieter, better side of the universe that is often missed, but very telling. It has shown us everything from the faint glow of ancient halos to the frantic birth of stars in dusty arms. If this trip through M33 gave you a better sense of our galaxy's neighborhood, please subscribe and come along on Beyond Horizons, where there is always more to discover in the universe.